We are waiting for some official people to arrive, and we already have the rector of the University d'Annunzio, who is organized with ICRANET and with the Commune of Pescara this event, which is just at the beginning. Questa è solo una piccola porzione dei presenti perché saranno 700. And we have to be thankful to the rector that he gave us the possibility to use the campus of University of D'Annunzio. It's not too far, but I think since you will be sitting for 4 hours here, and you will have lunch, it will be a welcome possibility to take a walk for 1 kilometer to just stretch before you start the second wave of conference in the afternoon. Therefore, be ready, don't make exercise while you are here, but you will have a great opportunity to walk to the other building 1.5 km away. Io ho detto di non fare gli stretch fino adesso, non preoccuparsi, perché possono fare 2 passi per andare al vostro centro. I am really extremely thankful to the rector, because it's a new university full of opportunity for everyone and also for us. And it's the first time that they start physics and astrophysics with this event. And since they are very close to ICRANET building, which is on the other side, but is in this direction, we hope very much to foster our collaboration. We are still waiting. Of course, we have to wait still a few minutes because the mayor did not arrive yet, but he can come in at any time. But there is somebody who has been announced many times that he's approaching and so forth. So let's wait at least for him, which is the president of the region, Abruzzo, which he wants to be present. Okay, let's wait for him. But the amount of news of this meeting are just incredible. Believe me, the results which we are going to present are truly exceptional. I announced to Rashid, he said, now he is convinced. I announced to Dili, now he's convinced. I will announce shortly with 5 slides. But I think at this stage, since we cannot wait any longer, I ask the rector to give us his welcome.
Thank you very much. Good morning, everybody. It's a real pleasure for me to be here and to give you my warmest welcome in our city, Pescara, and in our university. And it has been told that the buildings of our university are very close to this place. The only problem is it's not a really chilly day. So if you have to walk, probably you will have some problem, not for the distance, but for the temperature. Anyway, I am very happy because the keywords of my university are internationalization, culture, and science. And it is fantastic to see all these people from several countries be in Pescara discussing by science. Last year we had the night of the research in the Gabriele D'Annunzio University, and the title was One World, One Health, 1,000 Cultures. And this is my idea. 1,000 cultures will save the world, and we have to put together all our expertises, all our skills, and all our knowledge. So I have just to hope that you will enjoy the place, you will enjoy the meeting, and you will have the opportunity again to come back to our university. And in the name of the science, I think that these will be days of great relevance. Thank you very much.
Thanks again. We really appreciate. And I have to add a few words because ICRANET was conceived in promote diplomatic relation, not in diplomacy, but in science, and scientific diplomacy. And we think in this very difficult moment, we have the pleasure in the first row to see some of the leading scientists from all over the world. It will be nice to take a picture and then later to identify. But just to mention one of the speakers today, Professor Liang, who is here, and with one of the most important mission, he will speak later. But there will be also tomorrow a ceremony of the Marcel Grossman Award, which will be delivered to Professor Dili and then to Professor Caspi from Canada and from professor from US, which has been collaborating with us for many years, Orge, and Orge is in the first row, Chris Fryer from the Los Alamos Laboratory. And we have been collaborating very, very closely. Okay, we have to keep going. And as soon as the president of the region will arrive and the mayor will arrive, we will just ask them to give a brief contact. But I promise to make an introduction. Okay, let's see the introduction. Per favore. Ciano. L'altra sala, come la posso spiegare? Lo devo chiamare? Just a second. Introductory remarks. Since I was in Princeton many years ago, 50 years ago, I started all my lectures, 50 years, with the same slides. Dove si come si fa a proiettare qua?
No, lo devo mettere in regia.
Sì. Oh, santi Dio. Ok. Tu hai già dato la tua presentazione. Good. And the slides I will show you later is about the Crab Nebula. A beautiful slides. The Crab Nebula was observed by the Chinese on 4th of July, 1054. We are going back to that object today. And we have just published a paper which I gave you. You see, it's worth it. It's worth it to wait a few seconds because the quality of this screen give reason of wait a few seconds. And I have to thank the organization in Pescara to have taken this screen for us. The next slides, he took away kindly my, yes. In that, there has been a very interesting discovery in the crab, as you all know. In 1967, Hewish discovered a pulsar in the sign inside the crab. And next, we will have the first presentation about neutron star and the pulsar. The next one show another aspect about the Crab Nebula, the spectrum of X-ray emission from that nebula in the X-ray and in the JEV. This is known, there are 500, huge amount of publication on this fact. Next. And this is one of the original documents in 1054, which the discovery by the Chinese astronomer, which were the only one in those years, in 1054, to have the intelligence to take the data of a guest star, this beautiful concept, a guest star, and give the details after 23 days, the most intense part finished, and then for 650 days and so forth was observed. You will find in your a short article which was just published a few days ago. Next. Okay, this is the key point. The key point, you will be using this diagram over and over again in this meeting for 1 week. And I am sure you will understand the significance of this diagram. The significance is, first at all, the time. Once 10 seconds, 1,000 seconds, 10 to the 5 seconds, and then up to 10 to the 11 second. What means 10 to the 11? 900 years. Today, the crab. You see it. But you have another diagram where the luminosity is given. If you take the luminosity of the sun is 10 to the 33 erg per second. It's below. You have to go over to 10 to the 37, 10 to, what is a gamma ray burst? A gamma ray burst is an object which has the luminosity of the 10 to the 33 of the sun, and then you multiply by 10 to the 12, the number of stars in the galaxy, you have 10 to the 45. Here it is. But then you have to still keep going to 10 to the 51, and in this meeting, we will show the first example of a gamma ray burst at 10 to the 55 erg. No, è andato via qualcosa. What is the message? The message, but I need the figure because otherwise I cannot complete. The message is simple. is that when the crab was observed by the Chinese, it was the 4th of July, 1054 here. But since this supernova was a gamma ray burst, this is our new idea. There was a period in which the luminosity was still higher on the 3rd of July, and you will find very exciting, which shows that this first phase was catastrophic in Egypt, and so forth and so on. But this will be part of the meeting. But you will see this message very clearly, bit by bit, and enjoy. We are today, this meeting will be dedicated to the understanding of binary-driven hypernova and to black holes acting to generate the energy here, which was caught, unfortunately, in Egypt, and the plague came out thanks to this irradiation of JEV and TEV radiation of the early part, and that gamma ray burst, which was peacefully appeared in China, peacefully, on the 4th of July, on the 3rd of July, was worse than the Hiroshima bomb on Egypt, and the plague officially was announced. And therefore, this is the first case in which a gamma ray burst live together with us. Stop. Otherwise, okay. This gives us the opportunity to see the mayor. Il presidente dov'è? Presidente della regione. Sta arrivando. Okay, the mayor of Pescara, is a great pleasure to thank him. He has been very vital in continuing for 20 years the activity of ICRANET in the building which we have in the center that you will come, and I will like to ask him. By the way, he came to the Marcel Grossman meeting in Paris many years ago.
Grazie.
Sì.
Buongiorno a tutti. Per Pescara è un grandissimo onore e un grandissimo piacere poter ospitare questo meeting di rilevanza internazionale, anzi di rilevanza mondiale.
Pescara is very happy to have this meeting of worldwide relevance.
Pescara, una città della provincia italiana, oramai da quasi 30 anni ospita un centro di astrofisica relativistica grazie al professor Ruffini, e con questo centro Pescara è collegata con tutto il mondo in un'ottica scientifica.
Pescara is connected through ICRANET to the scientific world.
Ma oggi, con questa iniziativa del meeting Marcel Grossman, Pescara assume una rilevanza ancora più importante. Questo meeting si svolge in questo edificio che 100 anni fa era una fabbrica, a testimonianza del fatto che questa città ha avuto sempre la capacità di guardare avanti, di non fermarsi mai, di cercare sempre un punto verso l'orizzonte.
Pescara is always, as a town, looking to the future. And we have no time now to go into details, but we will have time to illustrate, like I did to Sunyaev, the unique personality of Gabriele D'Annunzio, who was founder of all this movement of Pescara, well known, but not enough publicized yet. And in that sense, we continue, the mayor said, this opening to the future.
Pescara è sempre stata la città dell'accoglienza, la città della pace, la città in cui tutti hanno trovato un'opportunità di vita. Con questo meeting noi vogliamo testimoniare il fatto che attraverso la scienza tutto il mondo si può riunire in un'ottica di pace e Pescara vuole essere proprio questo, la città della pace, la città dell'accoglienza, la città della cooperazione nell'ottica della scienza come unione di tutti i popoli.
Well, this very nice. I think you have understood. Pescara has the possibility to have friendship, but and is friendly. Is friendly because accept people from all over the world together in this tradition, and want to project toward the future this spirit of open science as an organization.
In conclusione, ringraziandovi per essere qui a Pescara, nella nostra città, e anche augurandovi un buon soggiorno, perché Pescara è una città dove non soltanto si parla di scienza, ma è una città che ha delle bellissime cose da poter vedere. Museo dell'Ottocento, Museo di Gabriele D'Annunzio, Museo delle Genti d'Abruzzo, una splendida spiaggia e uno splendido mare. Concludendo, voglio parafrasare una frase del filosofo austriaco Wittgenstein, che diceva: ho cercato i contorni di un'isola e ho trovato i confini dell'oceano. Ecco, noi abbiamo cercato i contorni del mondo e stiamo cercando di trovare i confini dell'universo.
Well, I think you have understood, and let's thank him again. And never it has been so appropriate the sentence, because we are studying the confini dell'universo. Yes, in the first row you have people that are looking at billions of light years away. And if I can get back to my last slides on, this is precisely what is the case with, piacere, merci. The president of the region, now we can have a few words and then we start.
Thank you very much. Scusate per il ritardo, ma sono veramente orgoglioso di poter ospitare nella nostra regione un convegno di questo livello scientifico e con una presenza così ampia di personalità giunte da tutto il mondo. L'Abruzzo ha su questi temi, sull'astrofisica e sulle materie, sulla fisica teorica avanzata, una gloriosa tradizione che vede il suo epicentro nei laboratori di fisica nucleare del Gran Sasso, nell'osservatorio astronomico, nel Gran Sasso Science Institute, che è stato una istituzione costituita apposta dopo il terremoto per rilanciare nel segno della cultura e della ricerca scientifica lo sviluppo della città dell'Aquila e dell'Abruzzo in generale. Quindi si è creato un terreno fertile per far incontrare e far connettere le diverse esperienze da tutto il mondo che riguardano questi temi e questo ramo della scienza. Non parliamo poi di telespazio, del controllo satellitare, che vede nel centro spaziale del Fucino il suo punto di riferimento. Quindi siamo ben lieti di poter ospitare un evento che da questo punto di vista consolida, rafforza e rilancia una vocazione naturale del nostro territorio e della nostra regione. Quindi grazie e buon lavoro a tutti.
Spero che avremo più occasione di spiegarlo, quello che stiamo facendo in questa settimana. perché l'Abruzzo ha l'onore di avere tra i più grandi scienziati, oltre che 2 premi Nobel, tanti capi di missioni mondiali qua, che sono un altro settore che, di scienza avanzata, di comprensione dell'universo, che abbiamo sviluppato all'ICRANET. E questo è il 17° convegno mondiale ed è un tema che mi auguro possa risalire dall'Università d'Annunzio e dall'ICRANET anche sulle colline e le montagne dell'Aquila. Grazie. We can start. First speaker. Okay, 50 years. 50 years from the discovery of the first binary pulsar. Possenti will just guide us from this discovery, which celebrate today, 50 years of the binary pulsar. Okay, right.
Thank you, Remo. It's really a pleasure for me to have been invited to open this very exciting meeting. And I think that what I'll try to do is to take you through a journey from the beginning to the most recent year to understand some of the context. Today's celebrations cannot begin but remembering this, as Remo already did, the discovery of the first pulsar in 1967. Why this discovery is so important for physics? Basically, I answered with just one slide, which is the following. If you look at the rotational period of this pulsar, PSR J 0437 minus 4715, you get this number, 16 significant digits. It's very rare. Maybe there is just one other measurement in physics attaining this precision. Of course, this makes pulsars exceptional clocks for probing the space-time. And for doing that, you need a procedure, which is a technical procedure called timing. On one side, you have to repeat observations of your target, and then try to find trends in this in the times of arrival of the pulses from your pulsar. The key quantity in this context, just mentioning that since I'll come back on that shortly after, are the so-called residuals, basically the difference among the rotational model that you try to apply for a certain set of parameters and what you get from the observation. You'll never be exact in your prediction. The observation will always have some slight difference. Fitting from these for these differences allows you to improve your model and obtain the fantastic precision which I have shown before. Not all pulsars, unfortunately, are suitable for doing that. The majority, more than 3,000 nowadays, just checked the pulsar catalog yesterday, the so-called ordinary pulsars cannot allow to reach very high precision in your clock behavior, but luckily nature provided us with nowadays more than 500 objects which indeed are suitable for this kind of game. They are the so-called recycled pulsars. And 50 years ago, the first mildly recycled pulsar appeared in the landscape of science, the very famous first binary pulsar, PSR B 1913 plus 16, exactly 50 years ago. Not only the first binary pulsar, but also nature sometimes is strange because we haven't many of them, only 20 over more than 3,000 pulsars. Also the first observed the double neutron star system, in the sense that also the companion to this pulsar was a neutron star. And these are the prediction of the Einstein equations of general relativity about the orbital damping, the orbital decay of this binary system. Now, you can compare them with the measurement performed by these two guys, Russell Hals and Joe Taylor, and the yellow points are the measurement. I often show this to my students because this is a clear example of not a theory fitting the data, but the data reproducing the theory, which is very, very rare, even in current science. And of course, this showed that general relativity provides a very accurate description of the behavior or orbiting point masses whose internal structure does not affect the orbital motion. It provided the Nobel Prize to the two people here mentioned, and it was the first, some people say indirect, some other like me think that this was even a direct proof of the existence of the gravitational waves, which are the form with which the energy from the orbit is taken away and the orbit decays. Nowadays, the tests from this system are at the 0.16% level, but we have been lucky. I have also been lucky being part of this discovery. Since 20 years ago, we discovered another system, the so-called double pulsar PSR J0737-3039 A and B, which became the best laboratory for doing this kind of exercises. And I'm now showing you the same plot as before with the prediction of general relativity in red and the observations in blue color, just overlapping perfectly the prediction. At this point, we have been able to confirm this radiative prediction of general relativity at 0.013% level, the best attained test of radiative prediction of GR. The paper is 3 years ago by Michael Kramer. And in fact, there are many other very interesting GR effects in this system. And it will be a pleasure tomorrow to have Michael Kramer directly explaining to you at about 10 o'clock in the morning all these other effects. Meanwhile, pulsar science and pulsar observations went on. And in the last 2 decades, we have been able to transform the pulsar themselves into gravitational wave detectors. Sorry for the very toy representation of this kind of methodology, but I think it might be illustrative without going through many slides. Imagine you have the Earth and the radio telescope on that, and the radio pulsar, and a source of gravitational waves somewhere in the space. At this point, of course, the gravitational waves will affect both the radio telescope and the radio pulsar at different times, of course. And from this, along the line of sight from the radio pulsar to the Earth, the radio waves will have to surf these gravitational waves, getting a bit delayed or a bit advanced with respect to what would be in a perfectly flat space time. And we can measure this with the sensitivity, which can be expressed by this rule of thumb. The strain, the characteristic strain, the HC, at the frequency of the gravitational wave F, is, roughly speaking, the ratio among the uncertainty on your time of arrival, TOA, and the time span of your observation. If you are able to measure your time of arrivals with the precision of down to 10 nanoseconds, which can be feasible for some pulsar, and you have a time span of 30 years, you see that you can get an astonishingly small number for H, allowing to open the possibility to search for these gravitational waves. An instructive application was done more than 20 years ago now, when the radio galaxy 3C66 was claimed to host a double supermassive black hole binary of that huge mass. If that would have been true, the residuals, you remember, I anticipated them, the residuals in the times of arrival of your timing model for a given pulsar, in this case PSRB 1855 plus 09, should have appeared likewise at the bottom panel. But we are not seeing anything that kind. We are seeing a flat, scattered plot of residuals, which means that these supermassive black hole binaries cannot be there. But of course, you cannot trust in a single pulsar. You can use a single pulsar for putting upper limits on gravitational waves passing by, but not for detecting them. You need many pulsars for being sure that there are and can be there, unfortunately, additional effects which can mimic the gravitation, passing by gravitational waves. So you need an array of pulsar, and this is the idea of a pulsar timing array. You need to look at many pulsars repeatedly and search for distortion in the space-time which are common to all your radio pulsars. In particular, in this way, you can, looking at two pulsars and correlating their timing residual, two pulsars at an angular distance theta, one from the other in the sky, you can remove clock errors, in the clock at your radio telescope. You can remove errors in the solar system ephemeris, which are needed for translating the times of arrival of your pulses at the telescope to a common center, which is usually the barycenter of the solar system. And you might be left with a quadrupolar signature, which is the imprint of a gravitational wave underlying your observation. And this was first formalized by Ellings and Downs in 1983, showing that the green line here, is the expected correlation among a couple of pulsars. Each point here is the correlation among a couple of pulsars in the sky, separated by a given angular separation. This is the expected correlation in case you have an isotropic, stationary, stochastic, and I add unpolarized gravitational wave background underlying your array. This is the expectation. And what can produce this kind of, maybe you can click on the animation there, because I cannot do that from here. What can produce, for instance, this kind of gravitational waves? What we know is that, at least the current paradigm is that the galaxy assembled through a series of merging, including the black holes at their center. And when reaching a distance which is a sub-parsec, the two black holes, typically several millions or a fraction of billions solar masses, typically orbits at this frequency around nanohertz, scaled with the parameters which I have mentioned. So we expect to have gravitational waves just from the spiraling of these two objects in this frequency range between 1 nanohertz to 10, 20, 30 nanohertz. And of course, this is the frequency of the gravitational waves perturbing the space-time and leaving their imprint on your radio telescope times of arrival. And what is the spectrum of this gravitational wave background? I haven't time to go into details, but it's easy to show that you expect a frequency spectrum with a slope of -2/3 for the characteristic strain. And the maximum contribution comes from black hole binaries at around redshift 1. Now, you have seen that our aimed frequency is the nanohertz, 10 nanohertz frequency, and that nicely complements the interval of frequencies at which the other well-known and future detectors of gravitational waves are operating, the ground base, which already got a wonderful discovery, the future LISA space system, and even at even lower frequency, the cosmic microwave background will be in the aim. So we are in this range. Of course, our favored and most likely kind of sources are the already mentioned supermassive black hole binaries, but there could be alternative options, likewise emission from cosmic strings, from inflectionary era sources, and also the types of signals can be very different from a stochastic background already mentioned to periodic signal in case you have a close by supermassive black hole just now spiraling or even burst. Now, the experiments started in 2004 with the Parkes now Murray-Young radio telescope experiment, the Australian one. Then the North American experiment, NanoGrav, started 4 years later. More recently, the Indian team started its own experiment, and the Chinese pulsar timing array also entered in the game. And of course, which I'm mostly dealing now, is the European pulsar timing array, which formally set up in 2006, 2 years after the Australians. But indeed, given the fact that we already collected data since about 10 years before then, we have the longest data span among all the experiments. And all of this is conveyed within a single framework, which is called International Pulsar Timing Array, combining the data from all these experiments. The earlier results in 2015-16 were upper limits. And I here just list without commenting anymore the upper limits obtained by the different experiment and also by the combination of them. The most reliable, in my view, is not only because we did that, is this one, since we really put all the caveats in our calculation, a bit more conservative than other team. Latest results are indeed looking for the detection and not only anymore for simply upper limits. And I remind you that detection means detecting this quadrupolar correlation in your data. This is the prediction, and these are the results from the IPTA plus Indian PTA team. In green, again, the expectations, and in violet, the observation. Looking at the last 10 years of data, the Ellings and Downs green curve is reproduced at 3 sigma level with an amplitude of 2.5 times 10 to minus 15 plus minus something amplitude, which is compatible with our upper limit you have just seen. Okay, there are other features which I haven't time to comment. This is the spectrum, spectral index. You remember that I mentioned the spectral slope. When you convert that in a gravitational amplitude spectrum, the expected theoretical index is 13/3, 4.3 value, which is this line here. You can see that it is still compatible with the data, although maybe the data show a bit flatter spectrum than what is predicted by the simplest theory. And this last result from EPTA and INPTA have been nicely reproduced and supported by other experiments. All the papers appeared on the same day, late June 2023. The nanograph experiment, you can see that the amplitude and evidence are very similar. The Parkes experiment and also the Chinese one, although of course the experiment from the CPTA started later, and you need a long enough time span for detecting gravitational waves, which has a typical period of 10 years. And recently, we produced a common paper showing the compatibility of all these results. The paper appeared 1 month ago, 1 month and a half ago. And you see the sensitivity curves of the 3 major experiments. And there, the fact that both the spectral index and the amplitude of the signal are compatible within each other at 1 sigma level, a very reassuring outcome, since all these experiments ran on different data using different software and also sometimes different models for additional noise to apply to your pulsar. And in this same paper, it was possible to produce an expectation for what will be as soon as we will be able to join all our data, which we are now in the verge of doing. You see the signal-to-noise ratio of the joint all PTAs data will reach a level at which might be there will be no additional doubt on the existence of this signal, although this signal-to-noise ratio must be taken with some caution, since it is not yet corresponding to a precise false probability level, since we are running all the simulations for showing what a signal-to-noise ratio of 7 would mean in that context. However, the perspectives, as you can see, are very good for a final claim in a short amount of a year. Implication, I haven't time for doing many details on this, but first of all, the hypothesis that the source of this signal is due to superposing of many thousand of supermassive black hole binaries is still completely viable. If you can also extract some indication from the fact that the merger rate of these supermassive black hole binaries is probably in the upper part. This is the solid line is the result of the observation, and the field area of the prediction is in the upper part of the prediction from the model. There might be alternative hypotheses to the nature of this signal. Again, I leave you, in case you have questions, to be discussed later on, but all the other hypotheses are still viable, but you need to fine-tune a bit them for keeping them in the range of the possible sources: inflation, phase transition, cosmic strings, and so on. Also, the hypothesis of having as a source of the effect oscillation of the galactic potential in the presence of ultralight dark matter cannot be excluded yet, but it's important to note that whenever you add the presence of a gravitational wave background produced by supermassive black hole binaries to any of these models, a Bayesian comparison show that the gravitational wave background due to supermassive black hole binary dominates on the other source. So none of them can still be excluded, but still there is a tendency towards believing that the hypothesis of the ensemble of supermassive black hole binary as the source is the most viable. There are additional PTA experiments coming online. A very promising one is related to the Meerkat radio telescope in South Africa. And the future of this science will be even much more improved with the appearance of the SCAO, the big experiment, half of that in Australia and half of that in South Africa, which is due to come online with the first commissioning data in 2027 and at regime in 2029. And in this context, SKA will allow to increase the population of pulsar, and in particular, the population of the good clocks up to 1,500, and also will lead, we hope, to the discovery of some exotic system, including pulsar black hole. And the relativistic population of pulsar will also increase, and it will provide more than 100 clock with accuracy better than 100 nanoseconds that will lead to start a gravitational wave cosmology in the nanohertz range. Thank you.
Many thanks for very good review and very interesting. And we have 2 minutes for questions.
But I'll remain here in case they want later.
Please. No, you were first. Yes.
So my question is, what are the prospects for seeing individual events of individual binaries? You showed a nice example of an upper limit, but
exactly. They are not very high with this generation of a telescope, but even not negligible. If you are lucky enough, having a supermassive black hole binary not far enough, we could already see that. There may be some population synthesis were done, indicating that there is some maybe 3, 4, 10% probability of detecting that in the next 3, 4 years. Excellent. But depends if the nature will collaborate.
There was a question, yes. We have
very short note. The idea of the detection gravitational wave of binary black hole, for example, proposed by using the binary system or using the pulsar. It's proposed Mikhail Saj, Soviet physicist and astrophysicist, a lot of years ago when he was a postgraduate student as a pulsar discovery postgraduate student, Jocelyn Bell, but unfortunately he died.
Yes, unfortunately he had time to announce this idea.
Yeah, I totally agree. That's completely true.
Okay, please.
First, congratulations for the very nice results. About combining the result from different arrays, I think they share some of the common pulsars, right? So in a sense that they are not completely independent result. So when these results are combined together, how are these dealt with?
Yeah, so far what we did is comparing 2 by 2. In the paper, which I mentioned, appeared in last May, we used one experiment combining pulsar with the second and with the third. And we did that in all the possible combination. keeping all the pulsar for the first experiment, adding only for the second experiment, the one not in the first, and then doing the opposite, and then scrambling all around. And all this combination showed compatibility, which is really reassuring.
Thank you. Okay, we will go to the next.
You're welcome.
Yes. Do you hear me? I hope yes. Yes, Professor Roger Penrose prepared his talk for us as a video presentation. Therefore, may I ask you to show his presentation of great physicists. Please. Okay, is somebody responsible who will show us video? And Rama disappeared. It's coming. Okay, thank you. Да. Oh, thank you.
Hello, can you hear me?
Yes.
You can. Okay, shall I start the talk?
Yes.
Okay. Sorry about the confusion. You see the title I've given to the talk here is not actually one that I've given to you previously. It's to do with the puzzling contrast between the black hole singularity structure and the nature of the big singularity in the Big Bang. They seem to be completely different, and we have to try and understand what the basis of all this is. And I'm hoping that the theory of bitwisters, which I want to talk about at the end of my talk, could help in understanding this puzzle. Now, it's a very profound puzzle. Here I have a space-time diagram, roughly speaking, of the history of our universe. I've used this picture before often. I don't want to prejudice the issue as to whether the space is spatially closed or open. So at the back, you could imagine it keeps on going, or maybe it closes up. It doesn't matter in the things I want to say. Time is going up the picture, which is my usual convention, and the Big Bang's at the bottom. Now, suppose we had a collapsing universe, then that you would expect it to look like this if the whole situation is time symmetrical. But that's not what we see. What we expect to see is something very different, namely the congealing of a huge number of supermassive black holes. The singularity would be completely different, with the Weyl curvature dominating the situation instead of having the nice, clean, symmetrical situation before. So this is the actual expectation in our universe if it were collapsing. Of course, it's not collapsing. We don't necessarily expect that to happen eventually. But I just want to say that the expectation for a universe which was collapsing with black holes in it would be completely different from the picture we see. And we can understand that as the Weyl curvature going completely crazy, diverging madly, as one might expect from the Belinsky, Lifshitz, Khalatnikov model, Misner model of what would happen in generic space-time. But the question then is, why was the Big Bang not like that? So I just turned the picture upside down, and the expectation for a general situation would be a complete mess. Now, the usual argument that people tend to produce is that somehow in the very early stages there was an inflationary phase, and that somehow ironed the universe out. But that does not resolve this question. That is the picture that people produce. If we had a magnifying glass, we would see the thing looking a bit like the inflationary phase. But it does not explain why you don't get a situation like this. For some reason, even with the infraton field is time symmetrical. So why don't you get that mess? And the only calculations people do are looking slight perturbations away from complete symmetry, and that doesn't tell us very much. So it's a complete puzzle. Okay, let me continue. I think I'm going the wrong way here. No, that was the right way, sorry. Anyway, I want to address this question from a different perspective. Here we have a famous Escher picture, which the point I'm making is it's a conformal picture of hyperbolic geometry, but that's not relevant in detail. The main point I'm making is that you can represent infinity as a nice finite smooth boundary. And if you could use conformal geometry, you can often use this trick to make infinity finite, and so you can discuss it. Now here we have a Lorentzian. Hello?
It's okay, please continue.
Is it all right? Can you hear me?
Yes, we hear you.
Okay. Now this is just a picture of course, in space-time, you have a Lorentzian structure, you have a light cone, and the light rays are depicted there. And if you want to put mass in, then you can use these two famous formulae, Einstein and Planck together, which tells you that frequency and mass are equivalent. So if you really want a time scale, you need to have mass. If you don't have rest mass in your picture, then you don't really have this kind of geometry, and you might just have the light cones. Okay, so now I want to consider this space-time picture, and I've squashed infinity down to make a nice finite boundary. And I've also stretched out the Big Bang. This is an idea originally due to Paul Todd. Let me go back. I think I just want to talk about this picture. So that it looks as though one might be able to stretch the Big Bang out conformally. This is just a conformal picture. Or you squash down infinity conformally. And that's not an unreasonable picture of the universe we actually see. But the way you can only get away with this if the Big Bang is very much, as we seem to see, free of Weyl curvature. If the Weyl curvature somehow is squashed down to 0, and the Big Bang, not a generic Big Bang at all, then you would have a picture like this. But it doesn't explain why you have a picture like this. Why you get away with having this very, very special kind of Big Bang. And it's not part of the equations. The equations would allow that great mess, which I just showed you in the earlier picture. Now, what I'm trying to say is the reason that the Big Bang is of this very special character is that for some reason it's the conformal continuation of a previous eon. So the reason it's smooth and free of Weyl curvature is because it was the continuation of the remote future of a previous, what I call an eon, a cosmic eon. So our eon would be this middle one, going from here to here. And the argument is that there was a previous one which crossed over, and the reason that it's free of Weyl curvature is that in the remote future, that's just what you get. If you look at the Weyl curvature in an exponentially expanding universe with positive cosmological constant, then you will expect to have the Weyl curvature going away to 0 at such a rate that when you conformally squash it down, you do get a picture like this. So this is the idea. Of course, an idea like this needs more, not just an idea, we should need to have some kind of experimental confirmation of it. And in fact, there is some observational support. There are lots of crazy ideas we see in cosmology. Very few of them have any observational support unless they're close to the standard sort of picture. But what I am arguing here, that this model does have from two completely different kinds of observation. The first one of these rings, I don't want to talk about the observational effects at all here, but I just do indicate that there are these rings that are a prediction of the theory that if you have collisions between supermassive black holes in the eon prior to ours, then they would produce rings of disturbance in the cosmic microwave background. We might see them in one way or another, depending on which kind of analysis you're using. And there was two completely different kinds of analysis applied. One by Vahe Gozajan and myself, where we looked at low variance in the gravitational, in the cosmic microwave background. And the other one is looking for things called Hawking spots, which is a completely different prediction of the theory, the Hawking spots are, you have to look at what kind of disturbance would you expect in the very remote future of a previous eon. In the very remote future, you would expect that clusters of galaxies remain bound, even though the universe expands, and these clusters of galaxies remain bound, and they will develop supermassive black holes. These supermassive black holes will swallow each other until basically there's one left. This will swallow the stars. A good many of the stars will be swallowed by that black hole. Some will escape, but a good proportion of the stars will be swallowed. And so you will have a black hole of something of the order of a sizable galactic cluster. And in the remote future, these Hawking spots, well, what are the Hawking spots? You see those black holes will sit around and sit around until the Hawking temperature of the black hole, low as it is, will become lower than the background in the cosmology, and then the black hole will start to radiate away. It doesn't actually much matter whether that's what happens or not. You expect to have a spot in the remote future which joins onto the Big Bang of the next eon, and this will give you a hot spot in the microwave background. The hot spot will be stretched out by the time you see it, by the time that spot reaches the last scattering surface. It would be something like, well, what we see is something like 8 times the diameter of the full moon. Alan Guth pointed out that according to current theory, it ought to be only half that size. That's what I call the Guth anomaly. He's completely right. We were very puzzled by this at first. The size of the spots we see is actually twice the angular diameter that you would expect from ordinary theory. So you need an extended theory to explain why these spots are actually bigger by a linear factor of 2, roughly speaking. And this has led us to believe that there is a phase in the universe that hadn't been discussed before, which is what I call the gravitational wave epoch. Now, I want to discuss the gravitational wave epoch because this is what we really need in order to understand, first of all, the Guth anomaly, but secondly, to understand exactly how this transformation of this very, very remote, rarefied, cold future becomes indistinguishable from a Big Bang, which follows it. It looks like a crazy, completely, utterly different situation. One is extremely hot and extremely dense, the other is extremely cold and extremely rarefied. But if you have no mass around, then they're not so different, because as I mentioned before, what determines the scale ultimately is rest mass. And if you have no rest mass, then you can make a reasonable argument that the remote future does indeed look very much like a Big Bang. But we need a theory which copes with that situation. And really what I want to talk about is an idea for describing this phase in which the gravitational waves dominate and you have the matter content, physical matter, becomes not unimportant. And at that stage, you have a theory which describes that they really look very similar. The physics is very similar. So you want to make a theory which does this. Now I'm arguing that a way of treating this is this theory of bitwisters, which is really what I want to talk about. And I'm afraid I have to talk about it very rapidly because I don't have very much time. First of all, we start with spinors. And this is just a picture to describe the geometrical realization of a 2-component spinor. The 2-component spinors look like a flag, which is on the right-hand side picture. And this is on the celestial sphere. So the left-hand side, you see the celestial sphere, or it could be the antisphere, it could be the remote future sphere. And a point on that describes the 2-component spinor up to proportionality. And the factor of proportionality is determined, first of all, by the length of the null vector, which corresponds to that point. And secondly, the phase of that by a little flag plane, which you see as the flag plane on the right, and on the left-hand side, you see as the little tangent vector. I don't want to go into the details of that, but you can represent the two-component spinor there. Now you want to go a stage further to describe what I refer to as twistors. A twistor refers to a point. Well, you can describe a light ray by a twistor. That's what I've got in this picture. Here we have an origin to the, this is now Minkowski space. And I imagine a light ray going along, and you look at the future light cone of the origin, and you have one spinor which describes the point where this light cone intersects the light ray you're talking about. That's what I'm calling omega. And another spinor, which is called pi, which is the spinor attached to the direction of the light ray. So you have two spinors, omega and pi, which describe the light ray. And this is standard twistor theory for describing the space-time of Minkowski space. So let me continue. This is just the notation which I often use. Omega and pi together give you a twistor, that's Z alpha. The complex conjugate of a twistor is a dual twistor, and you reverse the alpha, the two spinors, and you take the complex conjugate of each. And then we have the twistor now has a Greek index, and the dual twistor is a lower index. And so you have the dual, the complex conjugates of the twistor. And then if you want a quantum theory of twistors, then you have this commutation rule. The twistors commute among themselves and the dual twistors commute among themselves. But a twistor and a dual twistor have this canonical commutation rule, which you see in the middle of this picture. Okay, so now what is a bitwistor? A bitwistor basically consists of a twistor and a dual twistor. So we say A alpha multiplied by the Z lower, and B lower beta multiplied by Z upper. And they have the canonical commutation rules. So a bitwistor really consists of a twistor and a dual twistor, that's A and B, and they satisfy the canonical commutation rules, which I just showed you on the previous slide. So that gives you the structure of the bitwistor space. And the virtue of the, let me just tell you the virtue of bitwistors as opposed to twistors is that you can, I can't quite remember which order I've given my slides. Yes, this is the last slide, but let me just go back to this in a minute. You see, you want to describe curved space-time. Everything I've said up to this point is going to talk about flat Minkowski space-time. If you want to like curved space-time, then twistor theory goes through fine if your space-time is what's called anti-self dual, which is a bit of a nuisance because space-time is not anti-self dual. In fact, it can't be real space-time and be anti-self dual at the same time without being conformally flat. So this very much restricts the applicability of twistor theory. Twistor theory does not directly apply in a global way to curved space-time for this reason. It has to be conformally flat, which is extremely restrictive. However, if you've got your bitwistors, then the bitwistors do apply, because what you find is, going back to the twistor theory, in order to understand what a twistor means geometrically, you really have to look at the complexification of space-time. And what the twistor represents is what's called an alpha plane. An alpha plane is a plane which exists only because the space-time is anti-self dual. So you want to have a formalism which does not restrict you to anti-self dual. So you do that by introducing bitwistors. So you have an A and the B at the same time, and the two things enable you to describe space-time. Well, for more or less for the reason which I hope I'll describe here. You see, I'd have to read what I've said, and that'll take me too long. But the idea is that the alpha planes and the beta planes, well, alpha plane corresponds to a twistor and the beta plane corresponds to a dual twistor. And if you have twistor theory, then you have to have those planes. And if they don't exist, you're in trouble. But in the case of bitwistors, the thing that plays the role of the alpha planes or the beta planes are the null JD6. And so your bitwistors still exist in a theory in which you have conformal curvature. So this is the idea. And therefore you can discuss the crossover from one eon to the next, where you have gravitational waves dominating in this crossover phase. And you want to have the big challenge, you see, is how do you explain a theory in which you can discuss the conformal structure of the space-time when the conformal structure is not conformally flat. And the idea of biotwistors is that you can do that. It enables you to discuss in a conformally invariant framework the space-time which is conformally curved. And that's the basic point I want to get across. In the CCC theory, that's exactly what you need. You want this phase where the gravitational waves dominate, and the biotwistor theory seems to be exactly the right tool to treat this. And when you have that additional phase where the gravitational waves dominate, you can understand why the Guth anomaly is explained and why the spots that we actually see with a confidence level of 99.98%. So it's pretty clear that there's something there. With this very strong confidence level, we get that figure, but with this wrong diameter. So you want to have a theory in which you explain why the diameter of these spots is twice as big as what we seem to see. And this requires not to have the kind of scheme which I used to have previously, but a scheme in which you have a phase in the universe, or an epoch in the universe, in which the gravitational waves dominate, in which case you now need a theory which can treat in a conformal way the conformally curved situation which you get in the crossover. And that's where the biotwistors come in. It's a program. I don't know how to do it yet. I haven't had enough time to think about it properly, but it seems to me it's a formalism which is sitting there waiting to be used for this particular problem. And I hope that somebody, whether I have a look at this properly, somebody else have a look at it properly, can understand how to treat the gravitational wave epoch and to explain how you get from one eon to the next. And it seems that it's worth doing because this theory, it does seem to give you things like these Hawking spots, does seem to give you these rings in the sky, which no other theory seems to produce. Other effects too, which I don't want to go into here. Thank you very much. Do I need to go back?
Are there questions? Yes, please.
Oh, sharing.
The question, yeah, in terms of your quest theory, whether you call the integrated gravitational interaction.
Oh, but it seems that nobody hears us.
Hello?
Hello?
I can hear discussion, but can you hear me?
Ask question.
In terms of your quest theory, whether you call the integrated gravitational.
Oh, wait a minute.
Yeah, sorry. Okay, hi. Can you hear me?
I can hear you. Can you hear me?
Okay, in terms of twist theory, whether you call the integrate gravitational induction with other solid basic interactions, electroweak and strong inductions, or you just use twist theory to describe gravitational induction. No way to integrate them together.
I'm sorry, I didn't understand the question. Can you repeat?
Okay, the question is in terms of your twist theory to
Yes.
describe gravitational interaction, whether you could use this theory to integrate the gravitational interaction with electron weak and strong inductions.
Well, nobody's worked on this as far as I know. I mean, you probably need biotwistors because, well, of course, electroweak, you have a handed theory, you have a chiral theory. I mean, which bitwister theory perfectly broad enough to handle theories which are chiral. It's just that the twister and the biotwister, sorry, the twister and the dual twister would not have a symmetrical role to play in the theory. I mean, nobody has developed twister theory to the extent in which you can talk about particle physics to this degree. It would be very interesting to do. And I think bitwister theory ought to have a role to play there. It's not been looked at, the theory is too young. But I could say one thing, that in bitwister theory, you have a natural triple product. So if you take 3 bitwisters, it gives you a fourth. It's like a vector product in ordinary vector analysis, but there you have two with a skew product, which gives you a third. But here you have a skew product of 3 elements to give you a fourth. Now, it seems to me that this is a nice vehicle for discussing SU3, because you can talk about the symmetry. There will be the planes determined by 3 vectors, and exactly how you realize them in terms of 3 individual vectors. I won't go into the details of this because it hasn't really been worked out properly. But I do think that bi-twistor theory also, quite independently of what I've been saying in this talk, could have a role to play in particle physics. And the first indication of that is it looks as though something like SU3 does have a natural role to play in the theory. Something like U1 does, clearly, so clearly electromagnetism does. Something like U1 does, something like SU3 does. I don't know if you talk about weak interactions, which is what the question was about. I don't know. It would be very interesting. There's no reason to believe that weak interactions could not also be handled within twistor theory, but it's all very young. These things have not even the strong interaction part of twistor theory, of bi-twistor theory, has not been worked out yet. The theory is much too young. I would hope that people could get involved in this and really explore how the techniques in the theory can be used and maybe applied into serious particle physics. It's not been done yet.
Thank you. Non-junk, please.
Very quick question. It's very naive. How can you distinguish between your CCC and the so-called standard inflationary model with the primordial gravitational wave detection or the CMB polarization detection? Can that be used to distinguish between your model and the so-called standard one?
Well, I say that one thing that distinguishes the model is the presence of the Hawking points, which we see with the 99.98% confidence level. The fact that they're there at all is not part of the standard cosmology. And the second one is the rings, which have been around much longer. Yeah. The confidence level for the rings is not so strong, but nevertheless not so weak. And when I say the confidence level, I'm referring to the Polish work headed by Krzysztof Meissner. Vahe Gozidan and I did a different analysis, completely different analysis, where we seem to see the effects, but we don't give a confidence level. The Polish people do give a confidence level. So if you ask me to compare these two theories, conventional theory simply does not have these effects. I don't see any role for the Hawking points, Hawking spots, I should call them. They're not actually points that you see. What you see are these little spots, which have a diameter of about 8 times the diameter of the full moon. And according to the Guth theory, they ought to be only 4 times the diameter of the full moon. So there's a little bit of a thing to explain there, which is partly what I was trying to talk about today. But nevertheless, conventional theory doesn't see the spots at all.
Okay.
And what's more is that inflation can't be there in this scheme.
Okay.
The effects of inflation, I mean, there are lots of things where inflation is supposed to explain, but the original argument is it tries to explain the uniformity of the universe, which it simply doesn't. Whereas this theory does explain the uniformity of the universe. There are details of inflation which you have to look at. Some of these, I think, are explained in CCC because you have a previous eon. You have these correlations between parts of the sky, which without inflation, you might expect not to be correlated. And inflation is introduced to say, well, these things have to give you correlations. But in CCC, you also have these correlations because they come about through the existence of the previous eon. All this needs to be looked at. I wouldn't say that the inflation against CCC has been studied because almost nobody has studied this kind of comparison. It would be very interesting to see in detail how the two behave. But inflation is completely inconsistent with CCC. If inflation were present, it would increase the gap between one eon and the next, so all the effects that we see would not be there. So inflation is inconsistent with CCC. And maybe a tiny phase of inflation would be all right, but anything of the degree to which inflation is considered in ordinary inflationary theory would be much too big, and this would destroy the connection between one eon and the next, and you would not see any of the effects that we do see.
Thank you. Thank you very much.
Okay, thanks for the question.
Yeah. And next talk is Remo Ruffini. Please.
Can I ask a question? I couldn't see in the last slide, the second last slide, you said it will be real if, and whatever the condition was, wasn't showing on the slide. Could you get me the slide so that?
You want to go back to my slides? I hope I can find them. You say this is a very late slide because that didn't have any pictures.
It's the one you say it would be real, the bi-twister would be real if. And then the next
something
thing,
is not there. I see. I'm so sorry. Was
couldn't
this the
see
second
that.
from the last slide?
Second last, I think it was it.
Can you remember the beginning of the sentence? I might find the end of it.
I think it is easier to reply by the letter exchange between you. Okay?
Okay, yes.
Because
about that,
without slide, it is difficult to follow.
I understand. Yes.
Thank you very much again. And you can write letter to Professor.
Thank you, yeah. I appreciate that. Thank you.
Thank you.
Yes. Now, Remo is speaking. Remo, are you ready? Next speaker, please. No, next speaker is Remo Ruffini, I think. Remo Ruffini, according to schedule. He is doing. Okay. Remo, maybe we will ask next last speaker to speak, or you're ready. Very long. Oh yes, Remo, you are already.
It was very exciting and hear the voice of Roger Penrose. And unfortunately, posso avere la prima diapositiva. And long ago, this picture is a good picture of the early, late 69, beginning of 70. And I was working with John Wheeler in Princeton. And next slide. And la prossima, per favore. And it happened that after visiting Moscow and speaking to Lifshitz about the geodesic around Kerr black hole, I hope Kerr will be here tomorrow morning, no, at least at a distance, that we managed to solve the geodetic motion and the circular orbit around the Kerr black hole. And Lifshitz was very kind to insert immediately in Landau Lifshitz. And this was not public because Wheeler did not want to publish, but I gave to Yevgeny, and he inserted right away in 1969. I stopped by on the way back in Florence, and there was a fantastic meeting by Roger Penrose at the first meeting of the European Physical Society. And Roger was presenting this idea, but the talk was stopped because they were the manifestation of the leftist student, and they were to stop. And then we walk out, and we sat in the seat of Piazza della Signoria. And there it was that Roger said, maybe you see the footnote which was added, maybe if you drop a particle and then you split the particle and you let that one particle going in and the other one coming out, maybe it's possible to extract energy from a Kerr black hole. This is in that footnote. Next. Next slide. Oh, santo cielo. Next, okay. But this idea, only recently I was thinking over, because I've been thinking this for 50 years. 50 years of this idea. 50 years. And we just solved a few days ago. And in the meantime, Misner Ton Wheeler published a book with creating the resentment by Kerr. Roy was very much against this. That you have an advanced civilization which develop garbage, and then if you have a rotating black hole, it can throw the particle in and use the energy of the rotation of the black hole to propel a civilization. I mean, if this in a book can find a politician that believes that and is dangerous. In the recent days, we went back to this process. Next slide. Next slide. La prossima diapositiva. No, per favore, quella dopo quella. Grazie. And I repeated with the help of a collaborator, looking into this Penrose process more in detail, and we discover something important, that unlike many people spoke against the Penrose process with three particles, a particle going in, a particle going out, a particle arriving, the first particle arrives, then it decays in split, one goes in the black hole, the other one goes out with more energy than the one coming in. This is well known to every person reading a book of physics. But if you repeat this process 1, 2, 3 times like Mr. Ton Wheeler proposed, comes out something incredible. Is that it violates energy conservation. Yes, you can extract the energy with one particle, with one system simple, but if you go to a repetitive process like Mr. Ton Wheeler proposed, you violate energy conservation. and there is a conceptual modification of the theory which is necessary. This is the key point that we understood only recently. And we submitted to FISREV letter in 2 articles which are under referee. Next. For the expert, they will enjoy to see this formula. For the non-expert, I think it's worth it for you to look anyway. But the key change in the physics of black hole, which of course was invented using the Kerr metric, was the work of Christodoulou in 1970, introducing siamo sicuri che non ce n'era una prima, dopo questa, va bene, introducing the mass formula of the black hole, which was done by Christodoulou and myself and Hawking, a few days apart, one from the other. And we always laugh about, but there was a stubborn position of Christodoulou. Christodoulou was very stubborn. Yes, yes, yes. We were first. 10 days apart. Then the key new point, I have no time because there will be plenty of seminar in the afternoon, has been the introduction. You know the mass m, the charge E, the angular momentum L, but there is another quantity which is crucial to the physics of black holes, which is the irreducible mass. And the irreducible mass is related to the surface of the black hole. And the irreducible mass always increases. Therefore, whatever particle goes in, and this has been one of the key points, it increased the irreducible mass and it increased the horizon and it reduced the ergosphere. And in addition, there were many periods of thinking about the formula of the black hole that we put also a charge, E. Many people in America complain about the charge of the black hole. I never answered, because I said I need the charge in order to have vacuum polarization, electron-positron plasma to create activity around the Kerr. One day we will explain. This was explained in 2020 by Rueda, who sits in the front. You don't have, like in an electron, you have the charge, the spin, and the magnetic moment. The same happens in the black hole. You have the L, and then you need a black hole not in vacuum, but with a background magnetic field. And then if there is the spin of the black hole and the external magnetic field, it creates like an electron. In this case, it's an effective charge. This is a very fundamental result. And then you can invert the formula 1 in the irreducible mass in form of ALM. And then you have a new concept, extractable energy. M minus M irreducible gives you the amount of matter that you can extract. And the amount of matter you can extract from a Kerr black hole is 29%. In the Rising-Nordstrom black hole, extremely. In the Kerr also is 50%. This is the new equation which we have been writing down in the FISREV letter paper. Next slide. No, there is a slides in between missing. ritorni indietro, prima ancora, veloce, prima ancora, sì, ecco. This is the paper in which everything was introduced. Let me spend a moment. This is paper by Christodoulou, and that is the paper, the same paper as figure 1 is the irreducible mass, figure 2 is the first example of the Penrose process which we introduced, the old way. You have the particle in, out, etc. We have verified this value today, confirmed that works for a single particle. But if you go to many particles, successive, one after next, doesn't work. It violates energy, and you have to consider the new physics. I will just show you the consequence. Next, let's go back to, yes. It's too much, impossible to go into the details. Fortunately, all the people who have participated to the FISREV letter paper, namely, in addition of myself, Quevedo, Rueda, Shurui Zhang, and well, you have seen in the title, are here to speak in the afternoon. Quevedo, Rueda, myself, and Shurui will speak in the afternoon. They will show you this diagram. For every particle mu1 going in, you can extract energy, but at the same time that you extract energy, the irreducible mass increase. The horizon increase as the ergosphere decrease. And for a single particle, this is easy and has been shown. The next slides, Prossima, shows the repetitive process which will be defined in the afternoon and illustrated by Quevedo, by Rueda and Shurui. But here is already the key point. The key point is that you have 1, 2, 4, 6, 18 particles, one next to the other. And what happens is that the horizon, starting at 1.2, the horizon grows and invade the ergosphere. And the extracted energy is represented down here, is not bigger than 3%. The next slide shows the greatest effort which was done by selecting the point of the splitting near the horizon, 1.2 of the size of the horizon, 1.4, 1.6, 1.8, and 2 is the surface area of the ergosphere and the horizon. And what this great diagram shows is that if you look at A, the blue line, you initiate with a Kerr black hole at A equal 1, and making successive process of emission, the angular momentum goes to 0. You extract all the rotational energy of the black hole. And if you look at the at the extracted energy, the one below, you see the green line below, here, the extracted energy does not go over 3%. In the meantime, the angular momentum decreases, and then the extractable energy also decreases, but I appreciate that very few of you can have the possibility to understand all this detail, but I just want to go to the conclusion. And what is the key result is that if you start from an extreme black hole rotating, which has M irreducible of 0.7, you see the green 0.7, that is the reducible mass, while the angular momentum decreases, while the extraction energy stays 3%, the irreducible mass from 0.7 goes to 1. This is the drama. What it means for you interested in black hole physics? It means that all the rotational energy of the black hole does not like to be extracted energy. You can extract up to 3%. Yes, that you can do, but not more. La prossima diapositiva. And okay, this is all the details to make this simple statement. And this is the most important table with Quevedo, Rueda, Ruffini, and Shugui Zhang, and they will publish, but there is also another co-author which has been very, very important in the Fizerev letter paper to do a lot of detailed computation. There has been a tremendous amount of computation on this. The next slide shows the conclusion. In order to evaluate the amount of the final extracted energy from rotating Kerr black hole, is necessary to ascertain if a transformation is reversible or irreversible, and then to establish the extractable energy. Okay, this is a statement. This means the table I have shown with the equation, all these equations have to be taken into account. The second point, if one address, and they will show in the afternoon, if one address solely gravitational interaction, in other words, the Penrose process, this is the key point. If you have black hole and gravitational interaction only, nature does not allow you to take out energy. The formula show that the M irreducible, first of all, cannot be neglected. And that both in a single and repetitive process, you cannot extract more than 3% of the black hole energy. What was unexpected before our recent work is that the final result of a repetitive process leads to extraction of the entire rotational energy, and the entire mass energy of the initial black hole consists only of the reducible mass. This was totally unexpected. You start with M, you go through the process. For every process, you increase for every process, you increase the horizon until you destroy completely the ergosphere. Dov'è? Là. And then instead, the only way, if you want to extract the rotational energy of the black hole, adesso, the only way to proceed is to have not only gravity, but to couple also to electromagnetism, a Kerr-Newman. Then if you do that, cosa è successo? Then if you do that, you can extract 50% of the energy of the black hole, but not by pure gravity. This is the most profound theorem we have found. Therefore, cosa è successo? Posso avere la... This is the most profound part of the result. And therefore, to extract the energy, what will be shown in the afternoon, it will be through the electrodynamical process, and there you can use the electrodynamical process. Vado avanti. Avanti. Yes, it's the case of Kerr-Newman black hole. Then if you pay with the background field B0 endowed with an effective charge, the rotational energy extraction process can approach reversibility. This has been proved in this recent paper. And you will feel free to, it's just an announcement of this. Because the paper are there, but the role of the irreducible mass is essential. The next, I want to close on letting people aware of what I said already this morning and announcing this exceptional result. This exceptional result of 3 gamma ray bursts, in which we see the extraction. In all these gamma ray bursts, we have 7 different processes going on, 7 different physical processes ongoing. The birth of the supernova rise, you will hear that in the talk of Wednesday by Wang Yu, and in 2 sessions tomorrow in the parallel session in this room. But what is fantastic is that we understand now completely 7 different processes in a gamma ray burst. And essential in the process of gamma ray burst is the one on blue, which is the Fermi-Lat of extraction of energy from the black hole. And in the UPE, there you see the extraction of energy due to the electrodynamics. And then you see the detail of the afterglow. But what is most striking, and I am very happy to show to one person here who is taping, Lipunov, is this fantastic component here in red and yellow. We discovered in 220101. Next slide. That yellow component in 221009, it coincides with the LAT data. Fantastic. And that is the only source which is 1 times 10 to the 55. I'm sorry with the chairman, but I have to conclude. The next one, you know, the first person who discovered this red component, it took quite a long time to put this in order, was the observation of Lyapunov in the optical with this all fantastic telescope playing around on planet Earth. But this source is the essential one. And now point is, he going back to the back and forth, if he was lucky enough, but first of all, Lyapunov was the first to make clear this. Let's go quickly back and forth from the tree. You see the red and the yellow. That one is the most energetic part of a gamma ray burst, which if he had been lucky to have the observation from Lazo, of course, Lazo was not on, they would have seen the TEV there, because the previous one, se possiamo tornare velocemente alle altre, here you see the Lazo data, and everything else is the same. And then again, if you go back one more, everything else is the same. We have a complete understanding of gamma ray burst. And I hope to have the time to explain to Nanzang this fantastic result. It's the first time we will have parallel session, we will have Wang Yu on plenary, we come back. Now, it is possible to extract rotational energy from Kerr black hole, up to 10 to the 51 erg. And we have the complete understanding of 7 different episodes. The key point is that you have to do the theory correctly with the reducible mass, but you have to go to the electrodynamics, not to gravity. Gravity does not allow to extract anything but 3% of the energy from a Kerr black hole by gravity only. It's a very fundamental theorem that in order to extract energy, you must have at least 2 different interactions.
Thank you, Remo. Unfortunately, Remo gave great talk. I was unable to interrupt him. Time for questions is out. It's impossible. Excuse me. Yes. Today we had great advertisement of a lot of talks, and I think that we already upload Remo, and he gave first introduction also showing this beautiful experimental data. As he thinks, these data are giving us a lot of information about gamma ray bursts, and this is very important. Okay, thank you, Remo, and we have the last.
We have the coffee break now.
Oh, we have coffee break, but do we have time for our last question? The last talk. We have additional one talk.
Can we postpone the talk after the coffee break? The last coffee break. Yes, but we reduce the coffee break. Yeah, but I want to, before you walk out.
Yes.
That gamma ray burst are present not only gamma ray bursts are not only present in the 1054,
yes,
but very possibly also in the Fermi bubble.
Yes. Thank you. This important statement. We have how many minutes when we start next talk? How many minutes? 5, 10 minutes for coffee? 15 minutes. In 15 minutes, we all join again for the last talk of our.
The coffee break, you can follow on either on your right or on your left and downstairs. Okay, the coffee break is downstairs.
Yes, ladies and gentlemen. Oh, please sit down. We start the last talk of morning session, and Professor Wu now already prepared first his slide. Please take your seats. And Professor Wu, thank you. You are already here. Oh, I can give you my own.
Okay, thank you. Okay, thank you, Chairperson. And also thanks Professor Ruffini for his invitation to attend this excellent meeting. So we all know Grossman. I just look at his contributions to the gravitational induction. There's 2 papers with Einstein we know. Okay, so my talk is about the several topics. The first is about the Taiji mission in China. So the discovery of gravitation. To the Einstein general relativity. So also brings us to study deeply the nature of space-time and gravities. So Taiji is a Chinese space-borne gravitational wave detection and leading by Chinese Academy of Sciences. So it consists of 3 identical satellites which form a equilateral triangle. Each of the satellites takes the Earth-like heliocentric orbit. The constellation will be leading or trailing Earth about 18 to 20 degrees. So the Taiji has the ability to detect the gravitational wave from intermediate and also supermassive black hole mergers. So about his brief review about the Taiji. So it started from 2008 for a feasibility study promoted by Professor Hu Wenrui. And then we started the K-technology development, especially 2011. We performed the preliminary design for a heliocentric orbit, the 3 million 3 million kilometer ambulance. Okay. So actually, it's 2012. I presented a talk in the first ELISA consulting meeting about space gravitational wave detection in China. So it's actually, so we have this preliminary mission. So that time, so especially we have sensitivities for intermediate black hole, or some sense for the seed black hole, then to understand that the supermassive black hole merges. Okay. And from 2011 to 2016, we have K-technology research and development, especially this mission was officially named as Taiji. So now we all know the Taiji. So Taiji is about the Chinese philosophy about origin of the universe, evolution. And 2016 to 2018 is for K-technology for Taiji programs supported by a strategic priority research program of Chinese Academy of Science. Okay, so there's a report from Nature in 2016 after the discovery of gravitational wave by the LIGO. And so the Taiji, we have the 3 satellites with armlands, with 3 million kilometers. So it's very quite similar to LISA. So LISA, we know the initial is about 5 million kilometers, and the 2011 is called the ELISA, about 1 million kilometers for armlands, and now is 2.5 million kilometers and armlands. So actually for the frequency is also similar. So launch time we should also be similar, yeah. And 2017, we organized an international symposium on gravitational wave at the University of Chinese Academy of Science. So we all agree to have 2 sets of space-based gravitational wave detection around the sun. Okay. For the Taiji technologies, there's mainly 2 parts. One is inter-satellite laser interferometer systems, which include the lasers, telescope, interferometer, and also drag-free control systems, which include the initial sensor, micro wrist, and actual stable platforms. Okay, so next stage is about the Taiji 1, which initiated in 2018 and launched in 2019. That just take only 1 year by the Chinese Academy of Science. So for the distribution of the pilot in Taiji 1, here is show you, so which actually test mainly for 2 systems. One is for optical metrology system, another is drug-free control systems. So actually all the pilots already tested, okay? So especially the on-orbit performance of Taiji 1 demonstrated the feasibility of pilot, and also the design, also manufacturing and assembling, and also adjusting of pilot, or if actually works, proved. So I just briefly review some results. So for example, the distance measurement noise amplitude spectral density of optical boundary interferometer is about 100 picometers, and the best precision could reach to 25 picometers in high frequency. And for the acceleration noise measured by the readout voltage fluctuations about 10 to minus 10 meter per second square. And also for this acceleration measured by the gravitational reference sensor, less than 2 times 10 to minus 9 meter per second square. Okay, and also the calibrated true wrist noise is about 0.15 micronewton, and also this residual acceleration of the satellite less than 10 to minus 8. Okay, some results already published in the communication physics, and also there's special issues which include more details, about 26 articles. And so actually the Taiji programs collaborations involve more than 180 members and about 13 institutions. Okay, for Taiji 2, now from 2020, so we carry out all the K technologies for both Taiji 2 and Taiji 3. So Taiji 2 as the Taiji Pathfinder is expected to launch around 2030. So Taiji 2 as the bridge between Taiji 1 and Taiji 3 to verify all the technologies for Taiji 3. And we may also have scientific outcome. So initially, the pilot for configuration of Taiji 2 is designed to be the same as the Taiji 3. So in order to expand to Taiji 3 for 3 satellites and for inheritance. Okay, so I just show the Taiji 2 pilot, which gave the research team, they already tested some prototype of laser interferometer and torsion balance with differential wavefront sensing techniques and the pilot integration schemes and so on. So following, I just show you pictures. So we may have some talks in the pilot session for more details for the techniques. So this for the interferometer for optical bounding, precise positioning, and then also this for the light head and the mirror and so on. And also for this ATP system, the acquisition with cameras and pointing with the DWS, and also for this initial sensor, capacitive sensing and electrostatic driving, and also for drug-free and thruster, where we take the cold gas thruster. Although we verified in Taiji 1 for this ion thruster. So, but for Taiji 2 and Taiji 3, we take a cold gas thruster. and also this pilot simulation, the quasi physical one, and also drag-free controller. So here's for the stable structure of satellite platform, some model prototype of Taiji satellites, and also thermometer, and also some test for this simulation for self-gravitational force. Okay, so also Taiji simulators, which include the simulation software and also four-link modeling and also sensitivity analysis and index systems. Okay. Okay, also for the data analysis, including the TDI numerical simulator for this Taiji Sim TDI. So the current situation for Taiji 2, we actually almost carry out all the technologies. It is ready to be approved by the engineering phase. So we should start the engineering phase B and as I emphasized, it is actually similar to the Taiji 3. This is because if we can have more extra budget, that could allow to have an additional satellite. So Taiji 2 could be extended to the mini Taiji with 3 satellites. And in this case, Taiji 2 could possess the capability to detect supermassive black hole merges. Although some sensitivities is relaxed by half order. Yeah. And some studies actually we have some papers published with Professor Han, maybe he could discuss in part of the session. And also actually in 2019 in the Xiangshan Science Conference, both Professor Vitali and Danzma as the LISA Pathfinder chief scientist and LISA chief science, they actually suggested us to replace the Taiji 2 with 2 satellites, 2 solid satellites, and from their experience from LISA Pathfinder. Okay, so actually we hold this conference. We discussed the mission of Chinese, the Taiji program, and the potential international cooperations. Okay, for Taiji 3 and the future prospect, and for science mission of Taiji programs, which actually focus on the sources for the supermassive black hole merging, and also the extreme mass ratio in spiral, and also galactic binaural, and some more sources like background gravitational wave, cosmic stream, even for the early gravitational waves for the ground-based detections, and may also some other new unknown gravitational sources. Okay, the roadmap of Taiji program, as I already showed, we have Taiji 1, the 3-stage roadmap of Taiji. Taiji 1, Taiji 2, and Taiji 3. So Taiji 1, we already tested. Taiji 2, we almost carry out all technologies, is ready to go next step. And we hope for Taiji 3, there's 1 to 2 years share with the LISA together. Because, yes, we already divided for technologies into 2 parts. One is for the ultra precise and K technology, as I discussed before. And another is ultra complex and K techniques. So for the space-based gravitational wave detection, there's a lot of source. So the problem is how to distinguish the different sources. And also there's the strong couplings of subsystems for the treatment of noise. Okay, some preliminary pilot requirements were already classified. And so why we should have 1 to 2 year share with the LISA together. So it will be good to have the Taiji LISA network. And the first step, and then for second step, we should have ground space joint observation. For the LISA or Taiji networks in space, it's called fast and accurately localize the gravitational wave source. And also that could reach several orders of magnitude improvement. And for science pond and the Taiji-Lisa network is highly possible to determine more precisely the Hubble constant up to less than 0.5%. And also the data of Taiji-Lisa network can be used to study the cosmology in more precise way and enable us to understand not only the nature of gravity, but also the expanding history of our universe and also our space-time. So then I briefly discuss what about the nature of gravity and the space-time, how to build a hyper-unified field theory. Okay. So the challenge is how to successfully combine the general relativity with quantum field theory and to study the unification of all basic forces. So we know the standard model in particle physics. So that's unify the three basic forces, the electron, weak, and stranded interactions by the internal gauge symmetries is 1, 2, 3, which is determined by the quantum number of leptons and quarks. Okay, so the direct detection of gravitational wave gave the crucial confirmation of Einstein's general relativity. The standard model of particles after the last particles, the Higgs particle discovered. So that model also precisely proved by experiment. Both theories actually consistent with experiment. The question, we cannot unify them together. This is because there are fundamental disparities in their basic framework. One starts from the geometry, from the coordinate system in Einstein theory, but another from the leptons, quarks, from the elemental particles. They're from different point of view. So here we want to, not like Einstein, we should start from the point, the notion is that the natural law stems from the intrinsic property of elemental particles rather than external geometrical properties of space-time coordinates. Otherwise, it's hard to unify both of them. So because all elemental particles, they should have all interactions, including gravitational interaction. And for leptons, quarks, we know in the standard model, so all symmetries and the basic force is determined by the quantum numbers like Halley spin, charge spin, isospin, color spins. Okay. So then we will ask question, what is symmetry indicated from quantum number of leptons, quarks to govern the gravitational interactions? Okay. So then we will show how the Einstein's equivalence principle will break down if we start from particles, from the intrinsic structure, internal symmetry of particles. Especially Penrose's singularity theorem implies a crucial challenge to general relativity. If we believe the reality existence of black hole and of our universe must not be singular. Okay, so we should go to beyond the Einstein theory. And the panelists discussed the twist theory. Yeah, I asked her question how to unify with the other interactions. So actually, we discussed the quantum field theory of gravity with spin, because in the standard model based on quantum field theory, which combine special relativity and quantum field theories, so based on the global flat spacetime. So we showed that based on the quantum field theory in flat spacetime to include gravity. So the only symmetry, only internal intrinsic property is spin of leptons and quarks. So we start from spin. So we will treat gravitational force on the same footing as the other three basic forces, electron, weak, and strong in the standard model, in a Minkowski flat spacetime. So that leads us to distinguish between intrinsic symmetries governed by part quantum numbers and the external symmetries describing their motion in coordinates. Okay. So then we have to introduce new concept of space-time. That means we have to introduce, I call it biform space-time with a five bundle structure. That's the mathematical language. That means the Minkowski space-time serves as a bi-space-time to describe the motion of elemental particles, and the spin-related intrinsic graphic gauge space-time, so act as like a fiber. So then, which allows us to describe a gravitational interaction within quantum field theory in the spin-related gauge symmetries. But for space-time is still globally flat, the Minkowski space-time for their motion. Okay, so then we can integrate general relativity and quantum field theory. We call that gravitational quantum field theory. Okay. Okay, so then we have the joint symmetries. So then in the biform space-time, and the coordinate in the coordinate space we have Pangala symmetry, okay, Lorentz symmetry and translation symmetry. But in the graphic gauge space-time, in the lepton quarks in the field, there's inhomogeneous spin gauge symmetry. So that is gauge symmetry, local symmetry. It's not global. Okay, and so that means the fundamental gravitational field is no longer the metric field, but actually is a graphic gauge field in the biform space-time. We call it bi-covariant factor field. So actually, the gravitational interaction involving leptons and quarks, which has spin, and also the spin gauge boson, they only involve the spin-related graphic gauge field rather than the composite graph metric field. Okay, so this is, we introduced the spin-related graphic gauge space-time, and that space-time is no commutative because this is the derivative in a graphic gauge space-time. They are not no commutative due to the existence of gravitational interactions. Okay, then we generalize the Dirac equation to the gravitational relativity of quantum mechanics. Generalize the Dirac equation with including gravitational interactions. And then we can derive the graphic dynamics in the gravitational quantum field theory. We call the gauge type of gravitational equations, which is quite similar to the Maxwell equation. So this is for gravitational interactions by covariant factors with conserved currents. So then people ask how we derive the Einstein equation. Yes, we start from this equation, we project to space-time, we then obtain the generalized Einstein equation with a symmetric tensor. But then we have another one is anti-symmetric tensor, which is beyond the Einstein equations. Okay, so then we have some new effects for this graph dynamics beyond the Einstein theory of general relativity. This is additional terms. Okay, so for this additional terms, the recent studies with my colleagues, so then we found there's 5 polarizations in this gravitational quantum field theory rather than 2 polarizations in general relativity. So that means we should have, we could test the 5 polarization gravitational waves, which include the additional 2-factor component and 1 scalar component. So this is by we're discussing in the part session by Dr. Da Huang. So the massless graviton is described by the spin-related graphic gauge field is no longer the metric field. Okay, with this framework, gravitational quantum field theory, we can unify all the basic forces, 4 basic forces. We call the hyper-unified field theory. That means we treat all the spin-like charges of elemental particles as the hyperspin charge. We call the Bose spin, Halley spin, chirality spin, iso spin, color spin, finite spin as the hyperspin. And then we unify all these independent degrees of this spin quantum numbers into a single column factor in the spinor representation in the high dimensional hyperspace time. So why the Dirac equation, the Dirac field has 4 complex components because it's a 4-dimensional space-time to meet the Lorentz symmetry. So the Dirac equation instead of Schrödinger equation, which has only single wave function. But the Dirac field has 4 components because of the 4th-dimensional spacetime. Now we ask question, if we unify all leptons quarks into a single particles, there's more independent degrees, and we ask it should be in which dimension spacetime it can move motion. And then we found there's 19-dimensional spacetime. So we can use the 19-dimensional spacetime as spinor representation to unify all leptons quarks into a single hyperspinor field. Okay, and in more general, we can provide the foundations of this hyper-unified field theory. We can start from a simple one. It's a simple hypothesis we call the maximum coherence motion, which include 3 postulators: simplest motion postulate, maximum correlation motion postulate, and a quadratic free wave motion postulate. Then we can prove why fundamental particles is spinor field, and then we can write down this the actions for this hyper-unified field theory for all basic interactions. Okay, and then eventually we found this extended symmetries is joint symmetry in a space-time. We have this general Pangala symmetries. In the graph gauge space hyperspace-time, we have inhomogeneous hyperspin symmetry. Okay, eventually we can get this gauge type gravitational equation for hypergraphic gauges field, and also we can derive this for symmetrical part is general Einstein equation. Then we have the anti-symmetric parts. Okay, let's finish. And we have a book actually for more detailed discussions. Okay, so I have no time, so we can answer at least all the questions to want to ask, including the dark matter candidate and the dark energies and so on. So eventually I want to say nature of gravity in Newton series, matter, space, and time are all independent we know. And the Einstein special relativity, space and time are related as being cosine space-time. In the general relativities, space-time is determined by the distribution of matter. In the gravitational quantum field theory, or hyper-unified field theory, space-time itself is a matter, which is the hypergraphic gauge space-time, which we have to use the diaphragm space-time concept. Thanks.
Thank you very much. I apologize. I think that we do not have time for questions, unfortunately. But you are here, everybody can come and ask you. This is the best. Then thanks again, and it's good. Remo, Professor Ruffini, may I ask you to tell about the changes in the program now?
Change the program because the next one I think should be about Federico. Are you there? Federico? Pronti, immediatamente. And then we will relocate Manuela later on as soon as we can. But in the moment, Abate, Wang Yu, and Mirabel. We have absolutely to finish. Scusami, adesso vediamo come fare.
Okay. Yes, you already announced. Yes, please start and ask.
Possiamo andare oltre. Quindi vediamo di farti parlare in pomeriggio eventualmente. Ma non ce la facciamo adesso perché siamo troppo in ritardo. Vediamo è proprio impossibile materialmente perché dobbiamo chiudere. Siamo andati oltre ogni. Sì.
Sì, abbatte, abbatte. Okay, thank you. So, this is, I can use this. Okay. The other direction. Okay, thank you. Now everything is working. So I would like to, first of all, thanks the organizer for giving me the opportunity to talk about the updates from Meerkat on pulsars. On pulsars. So in this talk, I will talk both about some of the new discoveries that were made with Meerkat and results from the timing of known sources. So first of all, in Meerkat is a radio telescope, is a radio interferometer located in the Karoo Desert of South Africa. It is composed of 64 antennas like you see here. Each of these antennae is about 13.5 meters in diameter. The maximum distance between these antennas is about 8 kilometers, and it operates in 3 frequency bands between 500 megahertz to 3.5 gigahertz. And in this, at this telescope, there are currently 2 main survey projects related to pulsars. One is called TRAPUM, which has the goal of searching for new pulsars in different environments. And the other one is called MeerTime, which has the goal of timing known pulsars to measure properties like, to measure things that I will show you in this presentation, like pulsar masses, tests of gravity, and pulsar timing array. So additionally, there is also another survey that is called the Max Planck Institute for Radio Astronomy Meerkat Galactic Plane Survey, or MMGPS, which is a dedicated survey in collaboration between the Max Planck Institute for Radio Astronomy in Bonn and the SARAO in South Africa, that is granted 300 hours to survey the galactic planes in all of 3 bands. And one of the goals of this survey is to search for new pulsars. So what are the fundamental science that we can tackle with the pulsars at Meerkat? So I've selected just a few examples. There are probably many more, but these are the ones I want to talk to you about. So first of all, we can test the equation of state of neutron stars. I will show you later how it's done, but basically it's about measuring masses and especially measuring the maximum possible mass of a neutron star. Then we can perform tests of general relativity in the strong regime in binary pulsars, especially binary pulsars with other compact objects. We can probe post-relativistic effects that have never been seen in other cases, and we can see them and test if general relativity predicts the right effect. Later, I will also talk about how Meerkat was able to update the binary neutron star merger rate to give more accurate values of the expectations of of how many binary neutron star mergers should happen and how many we should be able to see in the next runs. I will talk about possible connection between pulsars and FRBs, especially in the emission mechanism. I will also talk about another possibility that is arising with Meerkat and other radio telescopes, including also FAST, about probing the alternative formation scenarios of neutron stars. And finally, Andrea already introduced this this morning, but Meerkat is also worked in the pulsar timing array. So I will show you one slide with some of the results of this field. So first of all, the neutron star equation of state. So the neutron star equation of state describes the neutron stars in its entirety and depends on the internal composition, which is as of yet unknown. In this graph, we see the mass of a neutron star as a function of the radius, and each of these lines corresponds to a single model of the equation of state. There are many that overlap. But one of the important properties of these models is that they all have a maximum mass. Above a certain mass, each of these equations becomes unstable and the Newton star collapses into a black hole. So if we are able to measure Newton star masses and push the maximum mass to a higher level, we can exclude at least some of these models. And the value right now of the maximum maximum mass of Newton stars is about 2 solar masses. And so with Meerkat, we plan on improving on that. So how do we do that? One way of measuring the Newton star masses is by looking at binary systems with other compact objects. In this case, we can measure other than the standard Keplerian parameters, but in these objects, we can also measure post-Keplerian parameters. These include like the precession of the periastron, the orbital decay to the gravitational wave emission, and other distortions of the space-time caused by gravity. In this plot, we see an example of that. It's called the Shapiro delay. It happens when the pulsar is located right behind the companion at superior conjunction. And so the light from the pulsar has to travel close to the companion where the space-time is curved a little bit more. So it has to travel a little bit more time, more space, and time is also slowed down. So it delays a little bit. And we see this delay, that is the peak of this the peak of this curve, which corresponds to how much time later, with respect to where we would expect the pulses to arrive. Using measuring these parameters, Meerkat was able to detect and measure the masses of more than about 15 pulsars, with many more still unpublished. And one of them is likely to be higher than 2 solar masses, but I will not give the measures here because it's still not certain. But we are pretty sure that we can get a value higher than 2 solar masses. Another way of measuring masses is by looking at another kind of binary systems with non-degenerate objects. In this case, this companion is usually a main sequence star or a star that is at least non-degenerate, so it's usually much larger than the Newton star. So what happens is that in some cases, we see that the pulsar passes behind the companion and is eclipsed. So we see these eclipses. If we see the eclipses and we know how large the companion is, we can get an estimate of what the inclination angle actually is. And this is even easier to do in the case where we see eclipses in different frequency bands, especially in gamma ray, especially in both radio and gamma ray. So we can get a good estimate of the inclination angle. And this, coupled with the standard Keplerian parameters, can give us an estimate of the mass. This is one example, the most striking example that was found in Meerkat, a pulsar where the mass of the pulsar is found to be 2.06 solar masses plus or minus 0.13. So likely one of the most massive pulsars that we know of. So another very interesting example, probably one of the most striking example of discoveries by Meerkat, is this pulsar here called NGC 1851E, found in a globular cluster. That is, why is this so striking? Well, when we observed it, we measured that the eccentricity is about 0.7. So it's a very eccentric orbit, and the minimum companion mass, so the mass of the companion, has to be at least higher than 1.4 solar masses simply from the Keplerian parameters. By observing it for longer, we are able to detect the relativistic advance of periastron. And this, if you assume general relativity, tells us that the total mass of the system, so pulsar plus companion, is 3.9 solar masses. And this tells us that the companion mass has to be more than 2 solar masses in mass. And we know it's a compact object, so we have a binary between a pulsar and another compact object where the total mass is about 3.9 solar masses. Here you see the graph of the companion mass versus the inclination angle. Since in this case, we are only able to measure one post-Keplerian parameter, the rate of advance of the reastron, we do not have the exact masses, but we have found this range, which is still extremely interesting because the companion has to be between 2.1 solar masses and 2.7. This could either be, if it's on the low end, it could be the highest mass Newton star we've ever measured, or if it is a little higher, it could also be the very first pulsar black hole system that we have ever seen. The problem is that we do not know exactly the masses, so we do not know exactly if the companion is a Newton star, is a black hole, but by studying this object more, we can get a very precise, we can constrain the boundary between Newton stars and black hole with a much higher precision. So I also told you that at Meerkat, we want to test general relativity. One way of doing it, I suppose this will be explained better in a talk tomorrow by Michael Kramer, but I want to give you some updates from Meerkat. So one thing that we were able to do using observing the double pulsar was to detect next to leading order post-Keplerian parameters. So these include, for example, there are two effects that include the retardation effect due to the movement of the companion. So this means that while the light is being emitted from the pulsar and is traveling through the system, the companion is moving in that small amount of time, and we need to consider that movement to predict when the pulsar, when the signal will reach us. The other effect is that we see the deflection of the signal by the gravitational field of the companion. So we see the light bending. In the normal Shapiro delay, you do not see the light bending, you just see the light slow down. But in this, for the double pulsar, we're also able to see that the light is bending. So this is another effect next to leading order effect that we're able to measure with Meerkat in only 3 years. These effects were already measured for the double pulsar. This is not the first measure of these effects, but it needed about 16 years of other telescopes' time to measure these effects. And in only 3 years, Meerkat was able to measure them again with a higher precision. Another very interesting property of the double pulsar that is able to give us, that allows us to test gravity even more, is that it also shows eclipses. But in this case, the eclipses that you can see on the left are not caused by the companion blocking the light of the pulsar, but is caused by the magnetosphere of the companion. So the magnetosphere of the secondary pulsar is blocking the light from the first pulsar, and we see this stripy pattern that corresponds to the period of the secondary pulsar. By modeling these eclipses, we can measure the inclination angle of the magnetosphere of the companion, so we can measure also the geodetic precession of the companion and test the relativistic spin-orbit coupling in the strong regime with a very high precision. Another point that we were able to do with Meerkat was about the update of the binary Newton star merger rate. So this was done thanks to the MMGPS survey, the Max Planck Institute Meerkat galactic plane survey, only at L-band, where they scanned the L-band, they scanned the galactic plane, and discovered 78 new pulsars. One of these discoveries was a double Newton star system, not merger, that has this name. And by measuring the decay of the orbit, they were able to measure that this system will merge within 7 gigayears. This means that this system is one of the systems that is likely to be seen, not right now, but is a progenitor of a system that can be seen with LIGO and Virgo. So thanks to this discovery, we were able to update the Newton star merger rate, the global Newton star merger rate, and predict that in the current O4 LIGO Virgo Kaga run, we should expect to see about 10 of such systems with a certain certainty. I also told you that the Meerkat was able to find a possible connection between pulsars and FRBs. This was possible to the observation of this pulsar located in the Large Magellanic Cloud. This pulsar also is what is interesting about this pulsar is that it emits giant pulses, but single pulses significantly brighter than the rest. So you can observe these giant pulses that are hundreds of signal to noise. The signal to noise is about 100. Some of these pulses show that they emit in a very small frequency band. They are band limited. This is not something that was seen in other pulsars. We do not really have any example of other pulsars where this band limited emission is seen, but it is a regular occurrence in FRBs, especially repeating FRBs. From this pulsar, we were able to say that this band limited nature is caused by the pulsar emission mechanism and not by the not by the environment around it. So it's probably something in the magnetosphere of the pulsar. And that could possibly be a link to explain these same features that we see in FRBs. One other thing that I find particularly interesting is that when Meerkat looked at pulsars in globular clusters, it discovered some pulsars that were exceptionally slow. Slow in this case is about 100 to 100 milliseconds to 2.5 seconds. This is normal value for pulsars, but in globular clusters, we don't expect to see them. Such slow pulsars have been seen before, and there are some other cases from fast that break this record of 2.5 seconds. And they are exceptional because if we try to measure the age, the characteristic age of this pulsar, so when would they be born in the standard scenario, it suggests that they were born about 100 megayears ago, 200 megayears ago. The problem is that in globular clusters, there is no star formation. So there was no core collapse supernova 200 megayears ago that could have given birth to these pulsars. So this is a problem. There are deep possible explanations on how these pulsars could have formed. One theory is that these are disrupted recycling, but another theory that if confirmed could be very interesting is that they were formed recently, but not through core collapse supernovae, but through the accretion-induced collapse of white dwarfs. So they were not born from the supernovae, but they were born directly from a collapse to white dwarfs to Newton star. And if this is confirmed, it will be very interesting to see if these pulsars born from white dwarfs are the same, have the same properties as pulsars from supernovae. Finally, the last update that I want to give you about pulsar, this was already introduced by Andrea this morning, is about the pulsar timing array. So Meerkat is also monitoring a large number of pulsars, about 80 pulsars once every 2 weeks, with the aim of detecting ultra-low frequency gravitational waves with the PTA techniques. And Meerkat was active since 2018, so it only had about 4.5 years of data. But just with that, it was able to produce its own version of the Hellinks and Downs curve, so the correlation between pairs of pulsars. And in the case of an unpolarized isotropic stochastic gravitational wave background, you would expect the line to follow this line. So Meerkat was able to make this detection. If we take the values at this result at face value, it is a detection at 3.4 sigma, but there are a lot of caveats because there are a lot of models that need to be tested about other models that need to be tested. And so we need to continue working on this data. But if we were to add also this meerkat pulsar timing array data to the rest of the IPTA data, this would lead to a very significant increase in sensitivity and increase in detection capabilities. So what's going to happen in the future? So in the near future, we expect, as I said, to measure masses of pulsars above the 2 solar masses limit. We expect to measure additional next to leading order relativistic effects and do further tests of gravity. We still have the surveys made at S-band that haven't been analyzed yet. So we're expecting a lot of discoveries and possible mass measurements and possible other effects that we're not expecting right now, but we're expecting something to come out of these surveys. And finally, there will be further data PTA releases. So if we go a little bit further, in the next few years, Meerkat will be upgraded to Meerkat Plus. So this will be that 16 more antennas will be added for a total of 80 antennas. There will also be a new observing band at between 8 and 15 gigahertz, the band 5, that will be capable of doing pulsar research. And this configuration, given also the position of the Meerkat radio telescope in the southern hemisphere at a declination of about -30 degrees, is ideal for the searches in the galactic center, and especially searches for pulsars in the close vicinity of the supermassive black hole at the center of our galaxy, the Sagittarius A star. And this is the best option we have until now, the best survey that has the highest probability of detecting pulsars close to that, close to the supermassive black hole, and possibly even orbiting the supermassive black hole. Because the possibilities, the possible avenues of discoveries, if that is true, will be amazing, but we still have to find anything, and this is the best option we have until now.
Yes, this great example then everything is on time. Thank you. And are there questions? Yes, Liponov.
Not questions, notice.
Okay, please.
I have the two notices. There are a lot of observational facts agrees with the high massive Oppenheimer-Volkov limit for the neutron stars, maybe 30 years ago, because fast spin-up low magnetic neutron stars, which showed in 1985 by Friedman and co-authors in Nature.
Herbert Friedman.
And we, with Kostya Pasnov, we show that all neutron stars with a high Oppenheimer-Volkov have no any frequency more than 60-100 Hertz, 70-100 Hertz, nothing today. Nothing today is a millisecond pulsar with more. Is that another about the fast radio burst connection with the white dwarf? 2 years I sent paper with our team to the Van der Heuvel New Astronomy Review for this scenario, which firstly discussed in 1985 with Kostya Pasnov, formation of the strange X-ray pulsar 7 second, which spin down first strange X-ray, how to say, that magnetar. Later this show magnetar. During the induced collapse, very specific white dwarf system, very specific. oxygen, magnesium, very heavy, close to Chandrasekhar limit, and can be formated neutron stars.
Thank you. I
Thank you.
think that it's general remark.
Yes,
Everybody
it's,
heard it. Yes, please, are there other questions? Yes, please. Loud, please.
So I might shout then. Thank you for the nice presentation. Just one thing, concerning neutron star equation of state, we also are very interested in the radius because we can have a whole forest of possible equations of states. Is there any plan to address this with Meerkat, probably like with timing of eclipses? Because I see that as one of options which can be used to not to get an exact result, but to get like a upper limit. And second is more like also question related to this secondary alternative way to form a neutron star. What are the prerequisites of the white dwarf? That presumes it's like a heavier nuclei inside of it, so it cannot be like a lighter white dwarf accreting matter. So
first of all, about the equations of state, with Meerkat, with pulsar timing in general, it's usually not possible to measure the radius directly, but something I didn't tell you about the double pulsar. In the double pulsar, we can see some next to leading order post-Keplerian parameters, spin orbit coupling. So if we get a higher precision on these values, it is possible to get a value of the mass of the moment of inertia of the pulsar. So not directly the mass, but the moment of inertia, which is still related. So it's still an additional information that will be invaluable for models. But that is the only way to get a measure of the dimensions. Through eclipses is not really possible because you don't see the surface of the neutron star. You only see you see the magnetosphere. But of course, if you observe at higher energies, at X-rays, it is the best way of measuring the radiuses through the emission of the surface.
Excellent. Thank you. You wanted to continue. Excellent.
I think,
yes, I have additional very short question. These 16 new dishes, German dishes, are they the same diameter as others?
No, they will be 15 meters, and they will be the same dishes that will be used for the SKA.
SKA, and they have better surface accuracy because frequency channel is higher.
Yes.
Yes.
Yes, but these band 5 receivers will also be added to the current Meerkat. So
excellent. This is great new instrument and working very well. Okay, thank you very much again for your talk. And next talk is talk of Professor Wang Yu. Can artificial intelligence understand our universe? This really great title. Please. Please. Oh, there is a microphone. Please continue. You have 25 minutes.
Oh, okay. Hello, everyone. I'm Yu Wang. I'm working in ICRANet and enough. So clearly from the affiliation, I'm one of the very busy organizers whose mind is distracted by so many things. And finally, I have 30 minutes to concentrate on one thing of this talk. So my title is, Can AI Understand Our Universe? And the method we are using here is fine-tuning GPT by astrophysical data. Oh, thank you. So for over 400 years, physicists have always been seeking for the fundamental laws that govern our universe. This is the, no point. This is the known physics of the Lagrangians, of which the first 10 is from the standard model, which includes the strong interaction, the electron weak interaction, the CP violation, gravity, and the Higgs boson and others. These terms are relatively well understood and we can model. Then for the subsequent terms in the gray colors are those ones we know their existence, but we are not sure about their exact form. This includes the dark matter, the dark energy, the neutrino mass, the birth of the universe, and how the particles generated after the birth of the universe. And for sure, this Lagrangian is incomplete. There are some terms or even more terms that we are not even aware of their existence. And traditionally, for doing the scientific research, we have followed two paths. First is from the data. So we observe the data, then we abstract the data to theories. And the second path is based on the philosophical foundations or a very broad framework of thinking to guide us to conduct the theories. And for the modern science, I have collected many opinions from different scientists. I think most of us acknowledge that the data and the philosophical thinking are complementary. But the modern physics relies on the data more and more. This is a characteristic of our age of the rapidly advancing technologies. Now we have the artificial intelligence. So what can AI do on these two paths? So first, from the aspect of the data, AI can analyze a large amount of the data in a short while and accurately. And not only for the efficiency, it also looks at the data deeply to find a lot of details that may overlook by human. It also can do the simulation, especially for those data that the human found NCO problems. And the AI can also do the theoretical reasoning. First, it has the background knowledge. For example, it can explain all the terms of my first page of Lagrangian clearly and in detail. And the second, AI has the logic. It can think alongside with us. So sometimes AI can provide some ideas that we may miss. And AI can do mathematics. This is proved by, we know that the famous Fields medalist Terence Tao is using AI to prove the theory, and it works very well. So AI can not only do the data analysis, but also to do the theories. So the merge of the abilities of AI will signal the start of a new phase in scientific research. And this shift moves us from having specialized knowledge in various areas into an integrated understanding, offering a deep and more connected insight into how the natural world works. This is a very big plan. And the first step of this plan is to train a single AI to understand the various astrophysical data. And on November 30, 2022, OpenAI released the first version of ChatGPT, which is now being used by most of us, I think. So on this slide, the left side is the platform of the ChatGPT-4, and the right side is the cloud. These are the two most famous AIs currently. And they are answering the question of what is the large language model. So large language model uses language to communicate. And the language has the potential for our purpose. Because first, language is not only a tool to communicate, but it's also is a media for thinking. Thinking relies on the knowledge, and the knowledge is essentially some selected data. And the second, language itself contains a logic. So the model trained by the data presented by language inherently possess the logic. And the third, the large language model uses the transformer, the current ones, the transformer architecture, which is a general purpose network architecture, which is capable of dealing with different kinds of data and doing different kinds of tasks. And the fourth, the language model can use a plugin, and it even can write and execute the codes to do precise computation. Then what's the meaning of large in large language model? So first, large means it is trained by a very large big data set. So for the GPT-2, it has 1.5 billion parameters. But for the GPT-3, it has, GPT-3.5 has 20 billion parameters, and the GPT-4 that we are using now is estimated to have 1.76 trillion parameters. And the trillion is the scale of nowadays, of 2024. We see many models have reached such a big scale. And the second meaning of large is it is trained by a lot of data. So training a large language model essentially has two steps. Also, it can small. So the first step is called the pre-training. Pre-training is like the basic education. Think about the model as a student entering into a school, and it has to read a lot of books, including nearly all the knowledge on the internet, from the social media posts, from the Wikipedia, and all the articles from the archive. So by reading a lot of materials, it gradually learns the grammar, learns the structural sentence, and learns the logic. And a part of the parameters of this large language model is used for memorizing this knowledge. And another part, the other part is developed to have the logical reasoning ability. But so on the left side, it's a simplified version of the network for the pre-training. So we can see from the bottom side, there's a segment of the sentence composed of the word 1, 2, 3, 5 till n. And this segment of sentence is tokenized into some numbers, a series of numbers, which are fed into this neural network made of 24 transformers. Then the output is the probability of the next word. And on the right side, it's one example. And then we have the sentence begins with rainbow, red, orange, yellow, green, and the network should output the next word. So first, this sentence is tokenized into those numbers 3201, 8176, and so on. And the prediction, which is the output, is the probabilities of many words, of which the blue has the highest probability of 21.8%, and it is correct. The next color is the blue. And pre-training is very expensive and time-consuming. Normally, it requires thousands of GPUs running for months, and this is beyond the capacity of, I think, most of the scientific institutions. And for fine-tuning, the next step, so pre-training provides something like an undergraduate student who has the basic knowledges. Then fine-tuning fine-tunes this student to be a graduated student major in one area, because he will learn some specific data set of one area. So fine-tuning costs much less. The reason is the specific data set size is much smaller than the general data set. So the cost can be lowered down even lower than $100. And it only requires one GPU for some hours of working time. Now we are going to test if this fine-tuning procedure can make this model to understand the different types of the astrophysical data and give correct physical answer only by this one model doing all the things. So the first example is for the simplest one, the classification of the, and we take the gamma ray burst as one example. So gamma ray burst is divided into short and long GRBs based on the duration. And intrinsically, they have very different origins, the progenitors. We take the data from the Fermi catalog, which for each GRB has more than 300 features or properties. And then we only take 3 or 15, we select 15 features out of this more than 300. So we select, for example, the total counter rate, the fluence, the peak energy, the spectral index, and so on. And for sure, we have erased all the information related to your time. Otherwise, it's too simple for the machine. And on the left top figure shows the example of the 2 features. And we selected 1,200 random GRBs, of which 75% are used for training and the rest 25% are used for testing. So the step of training is like, first I tell the machine, or I ask the machine, I have a GRB with the properties of what. Can you tell me this is a long GRB or short GRB? And also during the training step, I tell it is a correct answer, like, oh, it's a long GRB. So after repeating this procedure for a few hundreds of GRBs, this model, the GPT, gradually adjusts its parameters to learn to recognize the classification of the GRBs. Then is the testing part that we test the remaining by only asking the model. So we have this data, then tell me what is the answer. And the right side collects the answers from the model by this confusion matrix. So finally, we have an overall classification accuracy of more than 90%. So only by training 1,200 GRBs. And the next example, we again using the same model. Okay, we train the GRB model, then we train other tasks on the same model. This again is a classification, but not from only 15 value, but from the spectra observed by the Sloan Digital Sky Survey to classify the spectra into 4 types of the phenomena. That from the top one, we can see the left top from the quasar, the galaxy, the star, and the broad absorption line quasars. This time we select 5 samples for each class. So in total, we will have 2,000 samples. And the right side shows, again, the confusion matrix. So we achieved 82% of the accuracy. This is relatively okay, but not so high. The reason is we have downsampled the resolution of this spectra. Because originally, each spectra has more than 3,000 points, but in order to control the cost, because it's very expensive to do the fine-tuning, we downsampled this high-resolution spectra to only 100 points. And we only selected 500 samples for each class. So we only used less than 1% of the data in size from SDSS, and still it has the accuracy of more than 80%. If we want to increase the accuracy, we can increase the resolution and put more data. The third example is for regression, and the simplest one to look at the redshift. Again, we are using the the spectrum from SDSS. Now we have here 4 spectra of the quasars at a different redshift by different colors. And the right side is the result. The gray points are the ground truth, which are the redshifts that are visually inspected by human being. And the green points are the model's inference. So you can see most of them are okay. And the relative accuracy rate is 90.66%. Now we go to the final example, that we want to infer the parameters of the black hole spin and the direction from the emission of the accretion disk. This example, after the training fine-tuning, this model achieved 100% accuracy for the spin direction. So the black hole's rotation with respect to the accretion disk. And also for the spin value itself, it has an accuracy of 98.17%, which is very high. So the result is on the right side. You see the predicted one and the theoretical simulated one almost overlap. So let's see the highlights comparing the large language model and the specific models of the neural networks. So for the large language model first, it only needs a very small portion of the data. As I mentioned before, less than 1% of SDS data is required. And the second one, this large language model, you only need to present the data to it 1 or 2 times. So it looks at data 1 or 2 times, then it understands. While the traditional neural networks, you need to repeatedly show the data to the neural network for tens or hundreds of times. And the third point, which is the most important one, so I marked the key point here, that the same model can perform various astrophysical data and give us a correct output. This is what we expected. So this is the foundation for discovering fundamental understanding through comprehensive knowledge. So I think our first test using the large language model is successful. So we want to have the model to observe more data to understand our universe deeply. So we need to provide the data to the model. So we are always talking about the large data. So what is the largest data? The largest data should come from all the observable universe. So if we stay on the Earth and only observe the phenomena on the Earth, we can only collect the data along this green line, which has the radius of 6,000 kilometers, the radius of the Earth. But if we look up, we look at the sky, our horizon will be broadened to 46 billion light years, which is the horizon of the observable universe. So we will not only have the data from the diversity of the lives on the Earth, but also the life and the life circles of the star, of the galaxy, and so on. And each of them provides a unique insight of the physical world that we want to understand. And for collecting the data, we need large scientific facilities. And luckily, I think nearly all the countries are spending a lot of money on it. Here are 3 examples from the road maps or the white books from Europe, from the United States, and from China. And we have a lot of big plans on the construction or already operational. For example, the bottom left one, the LST, it collects 1.5 terabytes data every day. This is impossible for human being to analyze by the traditional method. So they implement the deep learning a lot, and we have many more the satellites. So next, we are going to have some more philosophical discussion, but it's interesting. Because large language model, artificial intelligence, this is something new to us, and no one is certain about its future. So let's speculate it from the perspective of a physicist. So first, from simple to complex. The appearance of the world is complex. It has developed over billions of years. So from subatomic particles to the atoms and to the elements and the layers, by layers, we have the Earth, we have the galaxy. But all of these, they follow the same basic laws of physics, but resulting in increasingly complex ways. And for humans, when humans observe complex phenomena, and we will ask why. So we often break the complex phenomena down into simpler and understandable concepts. This is like we have a set of building blocks. When we were a child, we always play those building blocks. And the complex shapes are pieced together from some simple building blocks. And occasionally, we encounter new unseen shapes. So if our existing blocks cannot quite fit together to explain those new shapes, we are prompted to either looking for new blocks or breaking the existing ones into smaller pieces. So the more we look outward, that we observing more data, the simpler we explore inward, that we're looking for the more fundamental laws. And the theory of everything, that is the most basic building blocks, should be simple, comprehensible to every person. However, the search for the ultimate theory is difficult because the appearance of our world is complex to human. Therefore, what we need is not AI to help understand the ultimate theory, but rather to help find the ultimate theory. But once it found, both human and AI can understand. Then we propose an idea of how to train the AI. So if we view AI as an exceedingly complex function, then a serious expansion of the AI can promise numerous sub-AIs from the simplest zero-order AI to the more complex higher orders. So building on our previous discussion, that is the more data we observed, the simpler the building blocks will be found. So we expect that as a zero-order AI, sub-AI, after ultimate training, will be composed of very simple matrices. These matrices act as the fundamental building blocks, presenting the fundamental laws, which are then complicated by the higher order sub-AIs, presenting a complicated appearance of our world. And the advantage of this kind of explanation can solve two critical problems of the AI research that they are facing. So first is the safety of AI. So even if a human cannot control the entire AI system, we retain the control over the zero-order sub-AI, which is the simplest one and understandable by human. And without fundamental zero-order sub-AI, the whole system, the whole AI would collapse. And the second is how to train the AI which is smarter than human being. So when we are unable to evaluate whether the superhuman AI can be effectively trained by assessing its output, we can instead assess the changes in the AI's components, that is the matrices of the parameters. So using our very basic physical laws. For example, to judge based on whether the complexity and the orderliness of the lower order sub-AI's parameters conforming to the evolution of a statistical system. And this is the final page. In 1961, during a panel session on the future of physics, C.M. Young expressed the caution, suggesting that gaining a deep understanding in physics would become progressively more difficult. And meanwhile, Richard Feynman was optimistic, predicting that a final solution to the fundamental laws of physics would be found in 100 years. And in 2015, C.N. Young delivered a talk titled The Future of Physics Revisited. He pointed out that more than 50 years substantial effort only added to one deep level of understanding. And he speculated that reaching the next level of fundamental physics theory would take even longer, possibly more than 50 years. Now with the advent of AI, whose answer will be correct? Thank you.
Did you include Fermi paradox in your speculation?
So, Fermi paradox. So, okay. So can you explain in detail? So what's the exact answer?
I must to explain Fermi paradox. That's very simple. If the any
civilization, internal civilization.
no, that's your no. You know, yes. If absence of the civilization is a consequence of the no shifts of civilization in our solar system, because higher very because time of the understanding is much more shorter than Hubble time.
I didn't include these thoughts in this presentation, but I have my answer to this question. Yeah, I'm working on the gamma ray burst a lot. But I can show one. Don't have it here. You know, human, for us, we are, if we look at our civilization, we have developed for billions of years. Then how long we can still influence the future? It's not as long as the history of the observable universe. But we don't have a lot of the galaxies will depart. Yeah, the separation of the galaxies, yeah. So we don't have, so we are a civilization that we have to develop the technology fastly. Otherwise, we cannot influence other galaxies or a very far away universe. And for this question is, we also have a lot of the like gamma bursts, explosions in galaxies. And for human, we have very limited time. Yeah, I understand. Let me answer. Yeah. Yes. So my answer is based on gamma burst.
Okay.
No. But we can discuss later. Yes.
It's better to discuss later. Thank you for a very interesting talk again. And now time is completely expired. Let us. Yes, please.
About Wang Yu, I would like just to come back on one last point, Wang Yu. I'm Wang Yu. Yes, you were mentioning about the development of knowledge. I would not like to go to philosophical issue, but I would like to mention, I would not like to do philosophy, but I would like just to mention that some key idea, okay, and I would like to stress this, and you stress also in your lectures, some key ideas were introduced 50 years ago. But to understand the basic idea of 50 years ago, we had to develop a tremendous amount of technology, tremendous, which went from the first X-ray telescope to the large telescope to all the technology and data analysis. And it took 50 years. Now, if we keep going with more efficient techniques, maybe we will reduce that time. But the quantum time on the experience today, from the first idea of the black hole out of Kerr, 63, to today, you needed an enormous development in technology to pin down and realize the idea. I would like to insist on this, because I think this is reality. And I could have some idea 50 years ago. Was not possible to do the step we reached yesterday if we had not the enormous development of technology. And I think this brings up to the future. The future could be continuing, but we need a new technology to coordinate knowledge.
Thank you for the comments. Yeah, I agree. Yeah.
Excellent. Thank you. And next talk, the last talk of this session, is Professor Felix Mirabel.
Yes. Thank you. Okay. Well, my name is Felix Mirabel. I'm emeritus in the French Atomic Energy Commission and also in an institute for space research in the University of Buenos Aires. And I will talk about supermassive black holes and massive galaxies in the early universe. Where are we concerning this type of knowledge? I will not talk about small black holes, because the chairman of this session had very stimulating ideas of what will be the role of what we call microquasars during the epoch of reionization. I will talk about the supermassive black holes. And here I show a representation of our understanding. It's a very schematic representation of our current understanding of the global evolution of the universe since the Big Bang. Where due to the accelerated expansion and cooling, when the universe was 1100 of redshift, 380,000 years old, radiation decoupled from matter, and the universe was into a phase of space being completely pulled by atomic hydrogen. It's a phase called the Dark Ages, until the first galaxies and stars in those galaxies. I don't know what's going on. Yes, were formed when the universe was about 200, 300 million years old, and the intergalactic medium started to be ionized until it became almost completely ionized when the universe was 1 giga-year old. And this is the reason why we can see very far
until the formation of the first stars and galaxies. Now, one of the surprises that were produced before the James Webb Space Telescope came into operation was the detection of more than 300 supermassive black holes with masses up to 10 to the 8, even 10 to the 10, in quasars at redshifts in between 5 and 8. And this was a discovery from essentially ground-based observations, and obviously the community working in this area of research, all of us ask how supermassive black holes can grow up to 10 to the 9 solar masses when the universe was less than 700 million years old. And you can see here a diagram done in 2021 before the James Webb of how evolved the mass of the black holes as a function of redshift and age of the universe for the only 7 supermassive black holes with 10 to the 8 solar masses or more known at redshifts greater than 7. And the consensus nowadays, there are different models how the seeds of these supermassive black holes were formed, different models. I don't have time to go into them, but the consensus in the community is that supermassive black holes could not reach those very high masses from stars that had less than 100 solar masses. And the idea is that it was required that the seeds of these supermassive black holes should have masses greater than 10 to the 3 solar masses up to a few times 10 to the 4. And of course, the question, there are many theoreticians in this community, is how those seeds of supermassive black holes very early in the universe will have been formed. And there were seeds. One of the ideas is that they were of primordial origin. That was for first time proposed by Seldovich and Novikov in the year 1966, or of in the context of the cold and warm dark matter cosmologies, these seeds could be formed by direct collapse very early in the universe at redshifts of 20 or 30. So in the context of the lambda CDM model, the seeds of the supermassive black holes could be formed by direct collapse of streams of cold gas that merge in dark matter halos of 10 to the 5 solar masses at very high redshifts. And in fact, according to these models, these seeds will be formed by direct collapse of gas, of cold gas, before the bulk of the first stars, and will grow up much faster than the bulk of the first stars. And this model is being in some way confirmed by observations with James Webb, because among the black holes with redshifts in between 4 and 11, the James Webb find that they seem to be overmassive relative to the stellar bulk masses in the host galaxies, compared with the local relation of the black hole to the stellar mass relation. So when I was reading all this, I asked myself, I'm an observer, essentially. I asked myself, are there really turbulent cold flows converging in high redshift massive dark matter halos? Are there observations of this? And that was in 2022 when this paper was published in Nature. And the following year, it was reported in Science the discovery of cosmic streams of cold molecular gas converging in the massive dark matter halo that hosts the powerful radio galaxy called 4117 at a redshift of 3.8. This means when the universe was in between 1.5 and 2 gigayears, very early. And here you see a schematic representation of the observations, where you see the radio galaxy here indicated in the center of a cold dark matter halo, and that is surrounded by warm gas in Lyman alpha emission represented in red. That means there is a lot of massive star formations being formed in the halo of this galaxy. And then in blue, I call gas streams coming from the northwest towards this massive cold dark matter halo, and another one coming, converging from the southern part. And this is the paper published in Science, and it is this cold stream is merging, converging at the center of this cold dark matter halo at a relative velocity of 1,500 kilometers per second. So the molecular gas that is tracing this transition of neutral carbon, which has frequency of 492 gigahertz observed with ALMA, must be extremely turbulent. And these are observations that, if they are true, really confirm that numerical model published in Nature 1 year earlier. So the question is what the James Webb finds at even higher redshifts than 3.8. And recently, I think 1 month ago, appeared in the archive and a publication that synthesized a breakthrough workshop that took place in Bern about the first billion years according to the James Webb Telescope. And on the top diagram are represented in black the observations that were done with Hubble, essentially, as a function of redshift by dark points. And the red points or orange points are the observations now, after 1 year and a half of operations with the James Webb, with the discovery of 1,300 massive galaxies at redshifts greater than 6, 20 of them now spectroscopically confirmed at redshifts greater than 10. With a current galaxy, the most distant galaxy being at a redshift of 14.32. So only 20, in between 20 and 200 and 300 million years after the Big Bang. And the second diagram on the bottom revealed that according to the James Webb, there is a slower decrease of the UV luminosity function at redshifts greater than 8 than expected, which would imply that there is a more sustained early production of radiation due to an unexpectedly large number of luminous galaxies. So, and several people in the community, several groups said that is not possible because that may question the cold dark matter model of the universe. And several baryonic scenarios were proposed, but at the same time, teams that didn't participate in that workshop said that that these results, this flattening, you see the expected decrease as a function of redshift of the quantity of massive galaxies should follow this line. But with the James Webb is find this. And this was surprising, and another teams working also on the same subject say that these detections are real, and this flattening of the mass produced per year per megaparsec cube may be a real thing. So this is the debate that there is at this moment. And I would say that one can learn, apart from statistics, what is found in individual galaxies. And in fact, at redshifts greater than 10, there are very numerous bright and ultra-compact galaxies with sizes, with diameters that are smaller than 400 or 500 parsecs. And some of them host AGNs very early in the universe. So one of the questions for the following view graphs is that we still do not know what is the actual fraction of these very distant and compact galaxies that host AGNs. It is known that more than 10% must be the case, but it could be up to 50%, but this is still not solved out. There are massive galaxies with quench star formation as early as redshifts greater than 4. Quenching star formation means galaxies that have essentially died as star-forming galaxies so early. And this is something on which the whole community working in that area of research agrees. There must be something that makes that galaxies evolve and as the evolution is too much accelerated. And furthermore, dust obscure galaxies at redshift greater than 6 are found few 100 million years after the Big Bang. So the question that one can ask is, what could be the astrophysics mechanism that, in addition to gravity, enhance the formation and galaxy growth in the early universe? And one mechanism that has been studied in the local and even in the distant universe is feedback from black hole jets and associated outflows. The feedback from black holes could be positive in the sense that induce star formation, or negative. And that depends on the properties of the black hole jets and associated outflows, and very important, the column densities of the environmental gas. In high gas column densities, the black hole jets compact the neutral gas, inducing the formation of dense molecular clouds and therefore star formation. Whereas in low gas volume densities, the black hole jets heat and disperse the gas reservoir for the formation of stars. And this is well understood now from observations and models. And one interesting result from very recent by different groups of James Webb is that James Webb is finding that black holes in high redshift galaxies are frequently immersed in large column densities of atomic hydrogen. And this was done making models of the observed Lyman alpha drops here in all these high redshift galaxies. This is observed, and the models show that that the immediate column densities in which these central black holes are located must be greater than 10 to the 22 per square centimeter, which is enormous. So the quantity of gas that enshrouds the black holes is enormous, the density. And this implies that in those galaxies, taking into account the size, the fractions of atomic hydrogen, not taking into account molecular gas, must be greater than 10 or 50% the overall mass of the galaxies. Well, I have myself made calculations last night, and these column densities are more than 200, 2 orders of magnitude. The column densities, the mean column densities in the disk of the galaxy in the central part. So they are enormous. So therefore, according to what we understand from previous studies, black hole positive feedback is rare in the local universe because there are no such densities of gas, but must be very common in the early universe. And you have here an example. This is an example of the galaxy. This is a very nice case study. We can study the physics here. In the galaxy where I showed that there were streams of gas, the radio galaxy at a redshift of 3.8, it is found that in the last diagram there, that the Lyman alpha emission is produced from massive stars recently formed, is produced along the axis of the jets that emanate from this radio galaxy. I'm referring to this diagram. And more recently, it has been found using ALMA that not only stars are found, traces of newly formed stars being produced along the jets, but also very dense molecular gas, which is the phase previous to the formation of stars. And the star formation rates are enormous along these jets. In this case, it is estimated 250 million solar masses per year for the last giga year. And there is now another case like this at a redshift of 4.11, where star formation rates of 500 million years per year are found. So positive and negative feedback in the local and distant universe has been found everywhere, even in our galaxy. Now we have come to the the conviction that the microquasar that produce in our galaxy the apparent superluminal sources that was reported in Nature at distances of 40 parsecs of distance are found two star-forming regions produced by the impact of these jets producing bow shocks as in radio galaxies. And now with ALMA has been found that the molecular gas in this star-forming region follows the direction of the jets. And there are other cases, the classic Minkowski object, and also cases of negative feedback in the local universe and also at very high redshift. So the conclusion is that the AGN-driven outflows must regulate the growth of massive galaxies in the early universe. And this mechanism might be enhanced by the mechanism observed of gas-rich mergers that we know that trigger star formation. For instance, in the local universe, the most spectacular star formation rates are produced in what are called ultraluminous infrared galaxies that we know that are gas-rich mergers, 100% of them, and that drive during this merging cold gas towards the central regions of these galaxies. And here on the left, the comparison of one ultraluminous infrared galaxy in the local universe, and then another one being observed with comparable properties at a redshift of 9.3, and here another one at a redshift of 7.31. So the conclusion is that if the astrophysics mechanisms of AGN feedback and gas-rich mergers are taken into account, the James Webb observation of a very early appearance, fast growth, and rapid quench of luminous galaxies in the early universe may be some problem consistent with the lambda CDM model and not surprising after all. And I want to finish that, of course, there is a lot of work to do in this direction. And I was only meant by this talk to attract the attention of the opportunity for synergic cooperation between high energy astrophysics and high redshift research on the very early epochs of the universe. And of course, the importance of the mechanisms that I propose in this talk for this rapid growth or accelerated growth of galaxies due to AGN positive feedback. We don't know how important they are relative to the other baryonic mechanism that may play an important role in that epoch. Okay. 25 minutes. Yes, yes.
Questions? Okay, please, not jump.
That's a very nice talk. I see that you have done a lot of work over the past few years, including now the recent JWST result. Now, you can produce the seed black holes this way. Can microquasars also do the reionization efficiently in this way?
Well, I learned from our chairman that microquasars very early in the universe, what they produce, they heat the intergalactic medium essentially and contribute, but only partially in the reionization. I mean, the reionization at the beginning is mostly the massive stars, but microquasars are important because heating the intergalactic medium, the detection of H1 absorption at redshifts of 7 and so forth, as many projects are trying to detect, they are not detecting it because the gas is too hot due to microquasars.
Thank you for the nice talk. I agree with you. There's a lot of evidence for very many, high abundance of AGN at high redshift, and they could well have a strong impact. The seeding mechanism you mentioned, the Latif 22 nature study, whether you invoke these cold turbulent streams as a direct collapse mechanism or atomically cooled irradiated massive halos, the problem they all face is that they predict. It's very difficult. It's very uncommon to have these systems. So what they cannot do is predict the total number of seeds you need to explain the latest data. And I'll just advertise that this afternoon, the first STARS DM02 session, I'd encourage you to join. There'll be a lot of discussion about these topics.
Yes, yes, I perfectly agree with you. These halos are very rare, well, are formed very early in the universe. But there are observations that are showing that this is happening, as I have shown. Now, how important is, and in fact, these supermassive black holes very early in the universe, as were discovered already before the James Webb, they are very rare. If you count them per the density per unit volume, they are very, very rare.
Nice talk, Felix.
about 10 years ago, we have developed a theoretical model. Basically, it's in giant mass reservoir. You can form the in a sort of a direct, but it's a dynamic formation, time dependent, of supermassive black holes or hypermassive black holes, I call it. Say millions to several tens of billions, and from 10 to the 10 solar masses to even 10 to the 12 solar masses, or even higher. So the essential result is something the mass accretion rate is proportional to velocity cube divided by the gravitational constant. So if you put in, I'm a little bit conservative, using 1,000 kilometers per second for a cluster of galaxies. So you can form this supermassive or hypermassive black holes in the universe, including the early universe. Okay, so I will give a talk on that, but I think a lot of your description, we anticipate JWST to have very exciting results. Thanks for the talk. Okay.
Yes.
Yes.
First, let's thank for this beautiful talk, and thanks the chairman. But from the early days, when we started with John Wheeler introducing the black hole, we were thinking that black holes will form at the end of the thermonuclear evolution of stars. And we were forced by the observation of the latest data of our BDHN, that we have at Z equal 10 BDHN, which form black holes. But today, now you are bringing one step further, that black holes are not at the late stage. They are not only at 9 and 10 in BDHN, but they are even farther and bigger. Well, there is room for general relativity and astrophysics all over the universe.
Nobody is against. Okay, good. Then what is the program now? There is a break, or
there is break, and people who have lunch, they can have lunch. I myself drive you at the hotel, and we will meet again. Yes, and we will meet here in the different session, either at the university, or one session will be in this room and in the other room. But we will have a session in this room as well. But you have to go to the other university, to the other campus as well, for the parallel session.